ladies and gentlemen. So happy to see you all today. Good morning. The Future Science Prize Week opening ceremony will begin at 9:30. So please stay tuned, and also don't forget to turn your mobile phone to silent mode. See you at 9:30. Thank you. Hello, ladies and gentlemen. Welcome to the Future Science Prize Week. The opening ceremony will begin shortly. Please be seated. Don't forget to turn your mobile phone to silent mode. Later on, we will invite our VIP to the stage to have a group photo. Don't forget to put your badge in your pockets first. Stay tuned and see you in a bit. Ladies and gentlemen, the opening ceremony is about to begin. Thanks to the support of many parties, the Future Science Prize Week has been a great success. Please give a big round of applause to show your appreciation. Organizer, the Future Science Prize, and co-organizer, the Hong Kong Academy of Sciences, and our strategic partners including Sinogroup, Shangri-La Group, Tencent SSV Organization, the University of Hong Kong, the Hong Kong University of Science and Technology. Our partners include Qiming Venture Partners, 5Y Capital, Centerville, Future Innovation fully supporter, Leisure Science, Hong Kong Subsidized Secondary Subsidy Council, of and Novo, Trustar Capital, WeLight Capital, Alcoholic Capital, Cowlick Consulting, 1886 Holding Group, Tomocado, Computing Arts Lab, and our media partner, Radio Television Hong Kong, RTHK, and our funding organization, Innovation and Technology Commission. Without your support, the events would not be so successful. Once again, thank you so much.
科学的重要性是非常清楚了。没有科学的发展，世界不可能像今天这个样子。未来论坛创建这个科学大奖是一个非常有意义的事情，这是一个了不起的创举。
科学的作用最根本的就是扩展了我们人类对自然界的了解。科学是我们人类知识的边界，其实也是我们生存空间的一个开拓。
所以我们希望呢，这个科学啊，慢慢的成为我们现代社会的一个非常重要的一个文化，会对我们这个中华民族的兴起吧，会起一个非常重要的作用。
科学已经成了我生活中的一部分，而且是生活的一大部分。数学这种美比较，就是有一点阳春白雪的样子，比较抽象的美。然后一种绝对的真理。
很多做科学的人，包括自己在内，是可以从小一直有兴趣，一直到现在，或者一直到将来。
我小时候的理想，就是因为有那个科学的春天，正好在我小学毕业的时候啊，理想就是要当科学家。现在回过头来想想，那时候真是一个很幸运的选择。
它是一种探索，是一种创新，这种探索会是孜孜不倦的，会是勇敢的，甚至有时候是这个寂寞的。
科学跟技术的发展呢，其实是带来人类的文明的发展；技术呢的发展呢，带来的呢是一个渐进性的发展。但是呢，科学的发展呢是一个根本性的、基础性的发展。
我们用的 GPS 都用到广义相对论，都用到这个基本的一些物理原理，所有的一切都是用到科学。
中国最缺的就是那些核心技术，而中国核心技术的提升，一定要靠我们中国基础科学的研究的提升。
真正的创新工作的话呢，实际上是制定标准，不是跟着别人标准做。
一个是对在过去20-30年当中，中国在基础科研上面一些有原创性的、有突破性的，是一种充分的认可。这个也就是对将来我们接下来20-30年当中，或者接下来几十年当中，我们现在一批年轻人，就是需要鼓励他们去走原创的道路，鼓励他们去多做一些有突破性的工作。
科学是大国发展必不可少的重要的基础。 所以像我们中国这样一个大国，是不可能避开科学而成为真正的一个世界强国。
我们今天有很多企业家的楷模，但是我们今天需要更多科学家的楷模。作为一个这个投资人，我认为他必须有这样的一些远见，同时我认为也有一点责任去贡献更多，不管从资金上面还是从资源上面，去推动这样的一些这个科学前沿的发展。
在这个时间点，我们设立讲的，这更彰显了科技改变人类生活的这个重要性，真正的能够认可那些默默无闻的对社会做出巨大贡献的科学家，可以提升对他们的认知认可，
同时吸引更多的企业家、社会各界人士关注和支持科学家们的工作，促进科学成果的应用转化。
未来科学大奖是来自民间的，将会是国家、政府奖励科学研究、科技创新的有力补充。民间资本的介入，能使中国对科研工作者的奖励更加多元化。
任何一个奖，它的灵魂就是评审，不光是公正，关键还是它的准确性、它的科学性。这个评选的过程中，要借助全世界的各种专家来一起来评审。
我们靠什么规则来达到最大限度的共识，是一个技术性的问题，跟规则的建立是有关系的。我们就是确保每次开会、每次讨论，我们整个规则是得到严格执行的。未来科学大奖能够在今后的多少年里，是越来越得到公众的认可，越来越得到科技界的认可，使得它能够发扬光大，最后变成全世界范围内的人类的共同财富。
我们今天呢是在探索一条路，能够让企业家和科学家结合在一起，通过这种大奖的形式的话呢，给予科学家、给予中国的基础科学的研究呢给予支持。
这样的这个做法呢，完全是自发的。我们确实觉得，一个国家的一个创新能力，对国家的这种繁荣昌盛太重要了。做未来科学大奖呢，也是希望在这方面做一些尝试，
推动中国的科学的这个发展，与这个国力能够相称，使中国的这个整体的水平和竞争能力迈向一个新的台阶。
希望未来科学大奖能够成为国内乃至全球最具有影响力、最有激情、最好玩又最具有人文关怀的科学大奖，
成为华人对科学探知上一个里程碑的符号，能够让更加多的中国人通过这个大奖去热爱科学，
把这个科学的精神、对科学的了解、科学的热情传播到你的那个 community、你的那个朋友圈里去。
我们的科学家人才也会层出不穷，我们的全社会的这个科学文化素养也会进一步的提升，
可以激励很多我们将来的青年学生来投身到科学当中。
这个奖项应该像血脉一样往下传。这个背后，我觉得实际上是对一种科学精神一种启蒙、一种传承、一种强化。这样的话，这个科学奖项就不是嘉奖的一个刹那，而是嘉奖的一个时代，甚至是若干个时代。
有一句话叫以史为终，我去看了它100年以后的景象，100年以后未来科学大奖怎么样？那个时候人们会说，诺贝尔奖不要，我们要未来科学大奖。
我预祝100年以后，有一群中国科学家仔细看我们这个录像，然后回顾我们未来科学的大奖如何影响中国科学100年。
Distinguished guests, ladies and gentlemen, welcome to the 2024 Future Science Prize Week and the Science Symposium. It is my great honor to welcome you all. I'm the MC today, Yo Yilang. Hello everyone, good morning. Good morning. Well, today we're so thrilled to gather with many great minds of the year. The Future Science Prize Week aims to promote scientific spirit and pay tribute to scientists, leading the public to explore the forefront of world science with forward-looking perspective. This year, our program committee sets the agenda and invites domestic and international speakers to ensure the high level of academic content and extensive global perspective of the conference. To begin with, may I invite Program Committee Co-Chair, Professor Vivian Wing-Wai Yam, to deliver a welcome remarks. Professor Yam, please.
the Honorable Professor Xuan Dong, Mr. Ivan Lee, Mr. Eddie Zhang, distinguished guests, some of you have traveled from afar, colleagues, ladies and gentlemen, good morning. It's my great pleasure and honor to welcome all of you to the opening ceremony of the 2024 Future Science Prize Week. This event is jointly hosted by the Future Science Prize and the Hong Kong Academy of Sciences. In my capacity as the co-chair of the 2024 Future Science Prize Week Program Committee, together with Professor Douglas Lin, we would like to extend our heartfelt gratitude for your presence here today. Today marks not only the 9th year since the inception of the Future Science Prize, but also the 2nd time we host the Future Science Prize Week in Hong Kong. Hong Kong has a number of world-class research universities, with 5 ranked amongst the top 100 universities in the world. We also have outstanding talents in science and a supportive and rapidly developing environment of innovation. Among the 39 laureates awarded the Future Science Prize thus far, 5 of them are based in Hong Kong, so hosting this event in Hong Kong has a particular significance to many of us here. In the past 2 days, we have organized the Enlightening Science and Technology Forum and the 2024 Asian Young Scientists Fellowship Annual Conference. The first one in the Hong Kong University of Science and Technology and the Asian Young Scientists Fellowship Annual Conference yesterday at the University of Hong Kong. The Future Science Prize Week will have many more exciting programs to come in the following 3 days, from November 1st today to November the 3rd. Starting from today, we will have a 2-day science symposium that brings together top researchers from home and abroad, focusing on 5 key areas: chemistry, life science, physics, mathematics, and computer science, during which participants will share the latest cutting-edge research results. On November the 3rd, we shall have a dialogue section in which science-loving and passionate young people will have the opportunity for a face-to-face encounter and dialogue with our future science laureates, followed by the award ceremony at the Hong Kong Convention and Exhibition Center that will be the highlight of the week. Promoting science to achieve the future encapsulates our mission to harnessing the power of scientific knowledge and innovation as a driving force for shaping a brighter future and a brighter tomorrow. The Future Science Prize Week aims to highlight outstanding achievements in science, as well to promote the spirit of science. We strive to kindle the spark of curiosity in people of all ages, especially those in the next generation, our young people, to cultivate a passion for science and an eagerness to support scientific endeavors and to engage in scientific pursuits. I'm most grateful for the efforts and contributions of our committee members, section chairs, keynote speakers, panelists, our sponsors, and also our attendees. I would also like to thank our partners and supporting organizations in the mainland and in Hong Kong, particularly the Innovation, Technology and Industry Bureau, for their tremendous and generous support, and of course to the Hong Kong Science Museum and the Cultural and Leisure Department. I wish all of you a most enjoyable and inspiring Future Science Prize Week. So thank you very much. Thank you.
Thank you so much, Professor Yan. Please be seated. Thank you very much. Now we would like to invite Professor Xuan Dong, Secretary for Innovation, Technology and Industry Bureau, the government of the Hong Kong Special Administrative Region, to deliver an opening remarks. Professor Xuan, please.
Women, Lisa, Professor Lin, Professor List, distinguished guests, ladies and gentlemen, good morning. On behalf of the Hong Kong SAR government, I would like to extend my very warm welcome to all the scientists and speakers who are joining us for the 2024 Future Science Prize Week in Hong Kong. Last year, the Future Science Prize Week, or FSP for short, FSP Week, was held for the first time in Hong Kong, and it was an unprecedented success. Building on this fruitful experience, the Future Science Award Foundation and the Hong Kong Academy of Science jointly organized the FSP events in Hong Kong again this year, under the theme, Shining a Light on the Future of Science, bringing us with more new and exciting elements to the series of events. The Hong Kong Science Museum, where we are now, is one of the most popular museums in Hong Kong. Here, many younger generations, first exposed to science, sparking curiosity and igniting inquisitive minds, making it a perfect venue for today's opening ceremony and science symposium. To further promote popularization of science, the museum is also staging the 2024 The Future Science Prize exhibition, showcasing the research journey and achievements of the laureates, including our top-notch Hong Kong scientists. Indeed, we are blessed to have a wealth of great scientists and academics in Hong Kong who provide solid support for Hong Kong's journey towards our goal of becoming an international innovation and technology center, or INT center here, and an international hub for high-caliber talents. Just 2 weeks ago, our Chief Executive, Mr. Zhuang Li, delivered his 2024 policy address, where a number of new initiatives were outlined to further promote our INT development in Hong Kong. We will adhere to the principle of promoting technology with talents, leading industries with technology, and attracting talents with industry, and continue to perfect the INT ecosystem and enlarge our talent pool. Under one country, two systems, Hong Kong enjoys distinctive advantage of enjoying strong support from our motherland and being closely connected to the world, which is conducive to our global INT collaboration. The Hong Kong SAR government will continue to support the world-class INT events, just like FSP Week right here, and promote international INT exchange and the funds and technology for all to foster a favorable INT center in Hong Kong. Today's symposium will soon begin with the chemistry session. As Nobel laureate Marie Curie once said, "Nothing in life is to be feared. It is only to be understood." The scientific breakthroughs and achievements of our scientists provide us with a deeper understanding of the mysterious and unknown world. I believe that exchanges among scientists today will bring new insights and innovations, much like the transformative power of chemistry. I also hope that this event will become a beacon of light for our next generation. Before I close, I would like to thank Vivian and the organizing committee for orchestrating this impressive event. Please also join me in applauding the 2024 prize winner and our distinguished guest speakers. I wish you all a wonderful stay in Hong Kong and a rewarding exchange today. Thank you very much.
Thank you so much, Professor Xun. Please stay with us. Please stay with us. 请留步。 Please stay with us because we're going to have photo together. Thank you so much for your tremendous support. And before the group photo, just a warm reminder, you can take out your badge, then we can have an even better photo. Yeah, it will look even better, trust me. And then now we are going to invite more guests to the stage to join Professor Sun. Professor Dennis Low, Ms. Lisa Leung, Professor Vivian Yam. Continue your big hands to welcome our guests. Professor Lynn Douglas Nelson Joel, Professor Benjamin List, Professor Tony Mock, Professor Catherine Shah, Professor Chui Yi, Professor Anne Ferguson Smith, wow, today we have so many great minds, and then we are so excited to listen to all the sharing. And then Professor Lawrence Judah. We are so thrilled to have many guests travel to Hong Kong. Dr. Huang Xinyuan, Professor Nakajima Hidaku, Professor Tang Jinyao, and Professor Chen Peng. Thank you so much for joining us today. Thank you. Okay, now let's get ready. We can stand closer, and then please have a look to the center. Okay, one step to the left, right? May I invite you one step to the left, please? Okay, looks good. Okay, please have a look to our official photographer. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, a few more to go. And then please have a look, continue have a look to the center, please. Because we have so many cameras today, so after seeing the center, please also have a look to the, center, continue the center, please. 1, 2, 3, 1. Okay, have a look to the left, please. Yeah, we are keep rolling. Okay. Okay, thank you so much. Thank you very much. May I now invite Professor Sun, Professor Dennis Low, and Ms. Lisa Leung, please remain on the stage for the next photo. For the other guests, please be seated. Thank you very much. And then we are very happy to have many guests join us. We're going to invite 2024 Future Science Prize laureate, Professor Zhang Tao. And also Professor Li Yadong. Thank you for joining us. We're so thrilled to see you. And also, we are very happy to have many VIPs join us today, including Mr. Lee Kwok-pun Ivan, Mr. Zheng Kwok-chai Eddie, Mr. Lee Wai-Guan Lawrence, Mr. Choi Chi-man Samuel, Professor Wong Kam-fai William, Mr. Lam Jun-sheng, Dr. Hu Zhang-hong, Mr. Zhang Chi-shum Thomas, Mr. Zhang Ho-lai Jimmy, Professor Mok Ai-ming, Ms. Kwang Si-yin Amy, Professor Tam Kong Heng Paul. And also Professor Xie Zuowei. And Professor Lo Chak-shing. Thank you so much for joining us today. Thank you very much. Okay. Okay, now please have a look to the center. Please have look at our official photographer. 1, 2, 3, 1, 2, 3. A few more to go. Okay, 1, 2, 3. Yeah, please have a look to the center. One more to go. 1, 2, 3. Okay. Please don't forget your big smile. And then, yeah, one more to go in the middle. And then please have a look to the left, please. Left, we have different angle to tell people our news and our events, and have a look to the right too. Yes, to the right too, we have some camera over there. Okay, all done? Thank you. Thank you so much. May I now invite Professor Sun, Professor Dennis Lo, and Ms. Lisa Lam. Please remain on stage for the next photo. For the other guests, please be seated. Thank you. And next, we are going to invite more VIPs join us. Ms. Li Yi Yang. May I invite Ms. Li Yi Yang. Professor Anderson Shum. Ms. Yan Kin Fun Alice. Mr. Chan Kin Tak Samuel. Yeah, don't miss your big hands to welcome our guests, our hospitality. Ms. Wu Lai Wen. Dr. Yim Chi Sheng. We invite Dr. Yim Chi Sheng and also Professor Zhang Guangting Tim. Miss Emily Lau. Miss Ellen Lim. Mr. Richard Liu. Mr. Dan Gong. We invite Mr. Dan Gong. Mr. Tong Hefeng. Professor Li Wenzhang. And last but not least, Miss Kathy Wu. Okay, so may I invite one step to the left? Yes, perfect. This is just like our spirit. We even always want to strive for the best, even for the photo, just like our science spirit. Okay, please have a look to the center. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, a few more to go. 1, 2, 3. 1, 2, 3. Okay. Keep smiling. Don't forget your big smile. Okay, one more to go to the middle. And then have a look to the right. Have a look to the right, please. Yeah, you can chase him as well. Okay. Thank you so much. Thank you very much. May I invite you, please be seated. Thank you so much. So now, may I invite you all, please return to your seats, because we are going to have the group photo with all of you. So just remain on your seats. We're going to have 2 photos. The first photo, just wear your big smile. The second photo, we will have another gesture. So please get ready. Please be seated. Yeah, and then for those who are wearing glasses, you can adjust a little bit to look even more stunning. Okay. So let's get ready fast. Okay, which camera we should look at first? You are all the stars. Yeah. Okay, so, okay, we have just a moment. We cannot miss anyone. Okay. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, few more to go. Please have a look to the center. Don't forget your big smile. 1, 2, 3, 1, 2, 3. Okay, continue to have a look to the center, please. Okay, now we have another photo with your thumbs up to boost the energy to make our science symposium even more successful. Okay, give a like to our science symposium. Yeah, thumbs up. Okay, one more to go to the middle. Is okay? Okay, thank you very much. Thank you so much. Thank you very much for joining us today. Thank you. So after the opening ceremony, we are going to have the upcoming session will be about chemistry, the central science towards interdisciplinary research. I would like to introduce with you Professor Vivian Wing-Wah Yam as this session's convener. She is the Philip Wong Wilson Wong Professor in Chemistry and Energy and the Chair Professor of Chemistry, the University of Hong Kong, member, Chinese Academy of Sciences, Foreign Associate, U.S. National Academy of Sciences, Fellow, World Academy of Sciences, founding member, Hong Kong Academy of Sciences, co-chair, Program Committee of the Future Science Prize Week 2024. Please give warm welcome to Professor Vivian Wing-Wah Yam.
Good morning, distinguished guests, ladies and gentlemen. It is my great honor to serve as the chemistry section chair to convene today's section and to see you in Hong Kong. First, I would like to extend my sincere welcome and gratitude to all of you. Thanks to the elaborate preparation of all our speakers and the effort of the organizers. I believe you will have an inspiring and enjoyable scientific section on chemistry. The topic of today's section is the central science towards interdisciplinary research. We have 4 speakers today. They are Professor Benjamin List, Professor Yi Cui, Professor Pang Chan, and Professor Jinyao Tang. So let me introduce the first speaker. The first speaker is Professor Benjamin List from the Max Planck Institute for Coal Research. In 2021, he received the Nobel Prize for his work on asymmetric organocatalysis. Today, he will bring us a fascinating talk about the universality of acid catalysis. So, can we invite Professor Benjamin List, please?
Wonderful. Thank you so much, Vivian. I'm always full of excitement when I have the chance to come to China, but Hong Kong, this is even more exciting. I feel the enthusiasm here, and this is coming from old Europe, always a great pleasure to be here, and I wanted to thank you, Vivian, for having me here today. So I would like to start out with my by far biggest inspiration, and my biggest inspiration is a chemical transformation that would be shown on the next slide. And it is actually photosynthesis. And I don't know how you feel about it, but for me, this transformation, which happens in the leaves of plants, this is a special type of plant, the moss, where CO2 and water, 2 of the most abundant and readily available and inexpensive material on this planet, are united with sunlight This is a thermodynamically uphill reaction. It needs energy, and light provides that energy to give, on the one hand, carbohydrates, like glucose, for example, a complex hexamer. And carbohydrates are the basis of all food we eat on this planet, in case you haven't known this. And as a byproduct, as a stoichiometric byproduct, as chemists like to say, oxygen is produced, the single source of the air we need to breathe. So two of the most important ingredients for our life are created in this one chemical transformation. Really, really remarkable. And I would claim here, this is probably the most important chemical reaction, chemical transformation, I should say, happening in our solar system. But it doesn't happen spontaneously, right? CO2 and water do not react in the presence of sunlight to give carbohydrate and oxygen spontaneously. It requires the help of enzymes. And enzymes are proteins that occur in our bodies and in all living beings, which are catalysts. And this conveniently brings me to my favorite topic, and that is catalysis. And catalysis, I think even for those who are not chemists, is the true transformative power of chemistry, as Professor Suden has mentioned before, because catalysis basically enables chemical reaction to occur. For example, A and B unite to give C by reducing the activation barrier. When you bring two molecules together, it requires a little bit of energy, and the catalyst can lower that energy and facilitate this chemical process, make it possible in the first place, in fact. But the special thing about catalysts is that in this chemical process, they're not being used up. The catalyst mediates the chemistry, but it is not itself converted into something else in it. And that in turn means a catalyst can do its job an infinite number of times. A single molecule of magic, as I like to say. You know, without the catalyst, nothing would happen, but with one single molecule of a catalyst, a huge amount of something valuable can be created. And that is the true power of catalysis. And this has led to the situation, actually, that catalysis is not only arguably the most fascinating science. I'm sorry, I hope I'm not insulting anybody, but I cannot understand how anybody can research something else than catalysis. It's my personal flavor. But also quite a relevant technology. I would argue, but challenge me if I'm wrong, that catalysis is the single most important technology for our human life on this planet. And there is no other technology that can claim to feed, to heal, to warm, to transport humanity in our goods, other than catalysis. And I think it's not shown here, but catalysis for the economically inclined people contributes to 1/3 of the global domestic product. Numbers in the trillions. As I said, I think the most important technology available. And I just wanted to give you one example of all these incredibly relevant transformations that chemists have developed over the years. And that is actually Fischer-Tropsch. Sorry, it's cracking, not Fischer-Tropsch. It's another way how to make gasoline. It's cracking. And cracking is actually the catalytic cracking, the process how we make fuels, gasoline, that transport us, our ships, our planes, traditionally our cars also. And cracking is done on an up to 1 billion ton scale, huge amount of crude oil products that are distilled and then cracked, form these hydrocarbon compounds, olefins and alkanes, in an incredibly large amount, and fuel our industry. And this is just one of the many examples that contribute to our global domestic product. I also would like to emphasize Haber-Bosch, with which fertilizers are made. And without Haber-Bosch, there would only be half of you in this room, because we couldn't feed 8 billion people on the planet. Oswald, of course, is important, and Ziegler-Natter, which was also discovered at my institute, the way how we make plastic is one of the most important chemical reactions that chemists are doing on the planet. Now, the interesting thing about this has been for a long time that chemists believed in all of these transformations we need metals as the key catalyst component. And this is also nicely reflected in the Nobel Prizes that have been given over 100 years, actually from 1909 until 2010. There had been, I think, 8 or 9 Nobel Prizes in the area of chemical catalysis. And literally all of these awardees received the Nobel Prize for work using metals as the catalytic principle. And that is something that, as a graduate student and later as a postdoc, surprised me a little bit, because it turns out that the enzymes that I've mentioned in the beginning of my talk, that nature has evolved to catalyze biological chemical reactions, those enzymes do not need metals as the active principle. There are definitely many metals that use metals, but not all of them. In fact, the majority of all enzymes are completely metal-free. And so with that inspiration, I found that proline, an amino acid, in a way kind of a simplified enzyme, a purely organic molecule readily available from nature, inexpensive, non-toxic, both enantiomeric forms are available. We make it even in our own body, can catalyze a very challenging aldol reaction. At the time, this was actually one of the most sought after chemical transformation, the direct asymmetric aldol reaction. The best groups in the world were working on it in Stanford, in Tokyo, in China, everywhere. People were trying this. And it turns out this simple, purely organic small molecule not only catalyzes this reaction, but it defined the state of the art. In fact, until today, some of these reactions are best catalyzed with proline. And that was kind of, in the beginning, it was kind of a bit sort of a surprise to the community, and people were rubbing their eyes and oh, like, interesting, a bit maybe the exception of the rule that we always need metals. And there was also criticism about the high catalyst loading. I mentioned a single molecule away from magic, but we needed one molecule to make 4 product molecules. That's far away from that magic. And that, of course, was criticized. But little by little, people began to realize what a powerful principle organocatalysis could be. And now it's actually the #1 field in asymmetric synthesis. Nowadays, no company in the world, no pharmaceutical, no chemical, no perfume, any company that makes molecules is not using organocatalysis anymore. And there's also, this is also true for all academic institutions that have organic chemistry. They're all doing it now. And one of the key contributions to this change has been the discovery of the utilization of this proline-catalyzed aldol reaction in a drug synthesis, the synthesis of darunavir. We all remember, of course, the COVID pandemic, which was horrible, of course. I don't want to downplay it, but there had been an even worse pandemic before in the 1980s. Some of the older people might remember it, HIV, human immune deficiency virus, a virus that is deadly, actually, and most people who get infected with it die from it, and for which there is no vaccine available, in contrast to COVID. But this is now handleable because of the help of pharmaceuticals like darunavir, which are designed by medicinal chemists and which are made by process chemists. And we were, of course, happy to see that this chemistry had found some use on a technical scale. It's just one of the early examples. There are now many, many examples of asymmetric catalysis on a technical scale. But what I wanted to talk about today is the universality of acid catalysis. And acid catalysis, of course, is just one aspect of proline catalysis. Proline is a bifunctional molecule. It's an amino catalyst, but also a Brunset acid. And what I'm so excited about acid catalysis right now was a simple realization that I had, and that is the vast majority of all chemical reactions can be catalyzed with acids. And there's a very simple reason for that, and that is all that acids need as the key element in their substrate is the existence of electron density. And I don't know if you know this, but all materials, all molecules, all substances, everything, every matter on this planet contains electron density. And so there is this potential for universality if one had good acid catalysts. And in addition to this, we can easily modulate the reactivity. So this is well known, of course, with the Brunset law. This is a law that was created by a Swedish chemist, Brunset, I think over 100 years ago, basically correlating the acid strength, and we all know acids, some are very strong and they can dissolve metals, with the reactivity in a catalytic reaction. And of course, as you might imagine, the stronger the acid, the higher the reactivity. The problem, though, comes from the selectivity that we also need in chemical reactions, right? We want to catalyze chemical reactions, but not randomly. We want to get one specific product, ideally one single stereoisomer. And that problem comes from the fact that, you know, a proton is a simple, small elemental particle. It's a sphere, it's tiny, and it can never induce any selectivity in a chemical reaction. So this is the reason why people, and this is an example from my laboratory, developed, inspired by the work of David Evans and of course many others before me, people developed Lewis acid catalysts, in this case copper triflate, and in order to bring in selectivity, they coordinate a chiral complex ligand around that metal. And then you have a selective acid catalyst, a Lewis acid catalyst. But the problem of this design, and it's an inherent problem that has been overlooked actually, that this ligand, in turn, is a Lewis base. So basically you mix an acid and a base, and that weakens again the acidity, the Lewis acidity in this case, and you have a weaker catalyst. And that is why you again need very high catalyst loadings. And in addition, you need to decorate your substrate. In this case, it's a ketone reduction with various activating groups, an arene, another ester group, a tert-butyl ester. Here you need a special reagent. And all these requirements, of course, limit the scope of this type of catalysis. And so we had recently, actually in 2016, a breakthrough in my group. Actually, it started in 2012, when we designed such dimeric imidodiphosphate type catalysts. And those catalysts have an acidic proton in the middle of them, right here. And then around that proton, we have created a chiral small molecule-based cavity that, like an enzyme, provides a confined active space in which a chemical reaction can occur. And the beauty of this design is that we can, by modifying this inner core substituents, oxygen to N-trifluryl, we can drastically vary the acidity. Here you have some common Bronsted acids, sulfuric acid, for example, you might remember from high school. It's a very strong acid that can dissolve many metals, very dangerous. You should never come in contact with sulfuric acid. pKa is roughly 7.6. Our acids are 1,000 times stronger, actually, this one here, and we can go even beyond that, reaching the acidity of those acids that people have called magic acids, the strongest acids that are known to chemists. Very, very reactive species, but also confined. They have this nice chiral active volume around them, enabling selectivity to be dialed in. And so I wanted to show you a few examples. I know some of you are not chemists, many of you probably, but I still wanted to share with you a few of these reactions that we can catalyze with these acids to illustrate the universality of this principle and the power of what these kind of catalysts can do nowadays. For example, Han-Yong Bae and I, we discovered an aldol reaction now where we don't use 25 mole%, so one molecule makes 4 new product molecules, but we use ppm level. That means 1 part per million. And in some cases, we could even go lower than 1 part per million, reaching kind of ppb type asymmetric catalysis, the lowest catalyst loading that has ever been used in any asymmetric catalytic carbon-carbon bond forming transformation. And what that means for the economists here, 1 kilogram of such a catalyst could be used to make a megamole. In this case, this would amount to 388 tons of a product. The global demand of a blockbuster drug would be in that kind of range. So you get a feeling of how powerful organocatalysis has become. Also, with Hui Zhou, she's now a professor at Wuhan, we found that these catalysts not only feature this high reactivity, but also a remarkable selectivity when it comes to unprivileged small substrates like 2-butanone in a hydrocyanation reaction. This is an interesting reaction because it can be catalyzed by enzymes, by metals, and by organocatalysts, but even engineered enzymes, the most sophisticated catalysts that humans can make and modify, cannot improve the enantioselectivity beyond what Hui Zhou has achieved and that we have just published a couple of years ago in a Nature paper. Moreover, we can catalyze chemical reactions that were previously considered impossible. The Narel to isopipetinol conversion, for example, was for 100 years considered an impossible chemical reaction for the simple reason that the product is more sensitive to acids than the starting material. Right? Acids are universal, and they can also, in principle, activate this one. But because of the confinement of our catalyst, the reaction stops after the cyclization to this extremely valuable product which now can be used to make menthol. Menthol has been made for over 100 years on a technical scale using chemical synthesis, but this route is, by definition, the shortest that has ever been realized. Moreover, we can make cannabinoids. I'm not sure about the legal status in China and in Hong Kong. In Europe and in Germany, at least, they're now being legalized. They're used as pharmaceuticals, for example, but also recreationally for relaxation, I guess. I've never tried these compounds. But we can now make them synthetically in a very straightforward two-step route, and there's $1 billion market for all of these three molecules shown here. And the almost last example is an application in whale chemistry. You might be a little bit surprised. The sperm whales are beautiful animals, probably also around Hong Kong. And the sperm whales, actually, they are not very good in eating. And that is because they have only this big mouth, and then they open the mouth and all the food comes in, but they cannot select the food, right? And what happens is they eat squid, and the squid has some bones and the beak also. They cannot digest, and it accumulates in their intestines. And what happens is they form these waxy-like rocks, and they can die from them actually sometimes, but also they can get rid of them sometimes. They lose these rocks. They swim on the ocean for a few years, sometimes decades, and then a fisherman finds them. This is a fisherman in Thailand, and he found this rock here, which weighs 3 kilograms, and they gave him $3 million for that rock. And why? Because the amazing thing, given its history, squid, whale intestine, and then sort of excretion, if you break this rock apart, you experience the most beautiful scent that you have ever experienced, and that's the scent of ambergris. And ambergris has as the specific component the key ingredient ambrox. And ambrox is this molecule here. And these rocks are so valuable because for hundreds of years, chemists were unable to make ambrox in a really competitive manner. And so we have now accomplished this. Just earlier this year, we have published the first catalytic asymmetric polyene cyclization of homofarnesol, which is this simple compound here, which BASF, a big chemical producer, the biggest in the world actually in Germany, they can make very readily, and we can catalyze now for the very first time with an organic small molecule catalyst, its cyclization to this beautiful and extremely valuable molecule. So with all these nice results, at some point I said to my group, how about we protonate alkanes? You know, very much like in cracking, the first chemical reaction I showed you today. Can we go ahead and protonate an alkane, maybe site selectively so, and then cleave to, you know, just the desired small molecule fragments? That was the idea, and again, people would say, yeah, it's kind of a almost crazy idea. How is that possible? Such a transformation, how do you protonate an alkane in the first place? Such a transformation would involve a carbon with 5 bonds to it. And if you're not careful and propose this to a German organic chemistry professor as a student, you will be kicked out of the examination immediately because they don't accept that concept, right? And on the internet, they would make fun of you and call this a Texas carbon because it's obviously wrong. You cannot draw a carbon with 5 bonds. But it's also somewhat ignorant because actually George Olah received a Nobel Prize in 1994 for his work on carbonium ion chemistry, as these compounds are called. So they are actually real, and he has shown these compounds exist. And so the idea then, of course, was, can we control the selectivity in hydrocarbon alkane cleavage with our ID-Pi catalysts? And I was telling my students, the day we will reach this goal, then I can retire. And that was maybe a decade ago or so. And unfortunately for me now, actually this is possible. And I have a little group at Hokkaido University at ICRAD, and we have now published our first science paper together where we could show actually we can enantioselectively cleave such purely hydrocarbon alkanes, first example of that type, where small organic molecules activate alkanes to give these branched olefins here in excellent enantioselectivity. So this paper was just came out. So now I have a problem because I told them I will retire, but officially I still have at least 15 years or so to go, so I have to come up with a new idea. And I wanted to share this idea with you Right now, we are sort of in a very early phase, and it's just sort of an idea, and it all centers around my fascination with photosynthesis. I don't know if you know this, but there are bamboo trees that grow, I think, 1 meter in a week or so. So they're incredibly amazing, because if you think about it, this material all comes from the CO2 from the air, right? There's 420 parts per million of CO2 in the air, and that is the source of all this matter that you see there sort of precipitating out of thin air. Just remarkable. And again, this is the chemical reaction. CO2 reacts with water to give carbohydrates that form the wood and all the other stuff, the plants, the leaves, and so on, and oxygen. They give us the oxygen we breathe. So the question is, this is happening on a 200 billion ton scale, in case you didn't know this, every year. In spring, the plants start to build their leaves on a 200 billion ton scale. Unfortunately then, in the end of the year, the leaves fall down, they rot again, and they form CO2 again with the organisms that digest it. So that's what photosynthesis does. Can we chemists develop an artificial photosynthesis that simulates kind of this process? And in its essence, the question arose for me, and I was surprised to find nobody else has really thought about this before, at least, I mean, not in the mainstream. And the question was, can we then split CO2 directly? Can we split CO2 into carbon and oxygen? I think that would be a nice and really challenging transformation. I hope I can inspire the next generation in thinking about this. I know it's a bit awkward. Maybe some of you think this is a crazy idea. How can you do this? This is obviously thermodynamically uphill. And we all know that carbon can be burns in the presence of oxygen to give CO2, right? So the reverse reaction is well known to us. How can you go in this direction? But my answer to this is, I can only cite Steve Jobs, who had said, people who are crazy enough to think they can change the world are the ones that do, right? So I would say in my language, a crazy idea is a minimal requirement for a revolutionary discovery, right? If it's mainstream, by definition, it cannot lead to a scientific revolution, right? So it's kind of a minimal requirement, but unfortunately, it's not a sufficient requirement. So it could also be a crazy and unfortunately stupid idea, right? So you're always sort of in this fine balance here. However, we have done the computation, and it's actually simple to do, of course. It turns out that this transformation, for example, to graphite and oxygen, requires a large amount of energy, I admit, 94.2 kcal per mole. But this is actually less than what is needed for photosynthesis. Photosynthesis requires more than 120 kcal per mole. So you cannot convince me that this reaction is impossible. It must be possible. And as another element of encouragement, the reaction is already happening while we are speaking. It's happening on Mars, and actually also in the outer part of our atmosphere. And the question for a long time had been, why is there oxygen on Mars? There's very little oxygen, but there is oxygen on Mars. And the question was, how does it form? Because there are no plants on Mars, at least not to our knowledge. And the theory was that perhaps CO2 in the atmosphere of Mars is somehow split into carbon and oxygen. And also there's a second pathway into carbon monoxide and oxygen atoms. And this was experimentally verified 10 years ago. So this transformation happens on a much higher energy level, 11.44 electron volts is required, but you also generate oxygen in an excited state and carbon also in an excited state. So that's why this large amount of energy is required. And our idea now is to catalyze this chemical reaction. And I know it's a bit of a crazy idea, but as I said, you need a crazy idea. Organocatalysis was a crazy idea too when I started out, and I have a similar feeling right now. And so what would be appealing about this transformation is we could stop climate change by picking up CO2 from the atmosphere. We could use the coal to generate energy. The technology is around, right? We know very well how to create energy from coal. And we could transform the chemical industry into a sustainable chemical industry by utilizing solar carbon to drive it. So that's my idea with which I wanted to finish. And I'm very happy that a big German foundation, the Werner Siemens Stiftung, they're located in Switzerland, are now supporting us with a huge donation. And for 10 years now, we have enough funding to investigate this question. And I would be super happy if all of you work on this, and if you discover this transformation. If we are discovering, I would be slightly happier because it would bring some new meaning to our old-fashioned name, the Max Planck Institute for Kohlenforschung. It means coal research, as Vivian has translated it. We never translate it, but nobody's doing coal research anymore at our institute. But if we make coal again, I think that would be, useful and to our naming. With that, let me thank the great team that I work with. They're from all over the world. There's always, I think now we're 1/3 Chinese people, and I love to work with them. I had people from Hong Kong, actually, and I love the enthusiasm, the passion for science that people have here and that I witnessed today. And I would like to thank them, the funding bodies that have supported us over the years, and all of you for your kind attention. Thank you so much for having me.
So thank you so much. Thank you very much for the very exciting and inspiring talk by Professor Benjamin Liss. So particularly, it's really gratifying to see how chemists is going to change the world. And we look forward to the photosynthesis with the new catalysts that you are working on. And everyone will be joining to do this. So let me introduce our second speaker today, Professor Yi Choi. Professor Yi Choi is the director of the Prelude Institute for Energy, founding director of Sustainability Accelerator, Fortinan Founders Professor of Material Science and Engineering, and Energy Science and Engineering from Stanford University. And today, Professor Choi will be telling us about reinventing batteries. That's very important. Thank you.
Thank you, Vivian. Very exciting talk, Professor Liss. That's a really good catalytic reaction session. This really fits very well for this year's Future Science Prize. We have two winners for physical science, Professor Zhang Tao and Professor Li Yadong, for winning the award based on their work in single atom catalysis. Now let me switch gear a little bit, but still falling into the domain of chemistry. Professor Liss is telling you, hey, atom-atom reaction, molecule-molecule reaction, building chemical bond, transfer the electron, forming that chemical bond. Now the topic of batteries is taking this chemical reaction, utilized in a fundamentally very different way. Instead of having the electron forming the bonding, you are actually taking the electrons, going to outside circuit, and doing the work, and come back to form the bonding. That's why you need to separate one full reactions into two half reactions. For students right here, this is the fundamental of electrochemistry, separating the path of how the electrons move and how atoms move, and into two half reactions. So this is driving by the really fundamental ideas. How could you use clean electricity to power the whole society? Falling into two categories of application. One is mobile, the mobility, cell phone, laptops, electrical cars, electrical plane even, may be possible in the future. The second is in the bottom is stationary energy storage, store electricity coming from solar and wind, integrating with electrical grid. These two applications really driving in the future, no surprise, each area will be $1 trillion market. So we all know 2019 Nobel Prize was given to these three pioneers developing lithium-ion batteries, using lithium ions as the cations to neutralize electrons, really bring up the mobility revolution. And then we ask the questions, what's next? Is it all done by lithium ion? The answer is no. So we are still trying to look for how much more energy we can pack into given size, whether it's by weight or by volume. Can you double or 4 times of current batteries technology? Can you really have much longer lifetime? Instead of a couple of thousand cycles, you go to about 5x to 10x more cycle life. Instead of 5 to 10 years, do you have never die batteries, let's say 30 years? This is necessary for grid-scale energy storage. What about fast charging? Can you charge within 10 minutes or 5 minutes? This is really means you're driving electrons. You're driving the movement of ions very, very fast. Again, coming back to the kinetics of the chemistry or electrochemistry. And can you enable complete safety? Batteries still burn. And for the very large energy storage system, this becomes a big, big challenge. The reliability of the electricity grid is not there, and the safety concern is there. And the cost, can we generate technologies that provide 10x lower cost compared to the current lithium ion? Get to about $10 per kilowatt hour. Then you can have seasonal storage. You can have storage everywhere. Truly enable the green electricity revolution. At the end of the day, anything go to the global scale require you think about materials availability, circularity. Professor Liz was telling you some of the big number right there, billion-ton scale oil and gas industry. Billion tons is going to be the unit for you to go to global scale. The current lithium-ion battery production, we are only talking about 5 million ton yearly production. We are about 3 orders of magnitude away. But how do we obtain so much lithium, so much cobalt, nickel, and so on? That's not a trivial question. This requires new abundant chemistry. Need to think about circularity. With these challenges in mind, maybe let me share with you in the next about 25 minutes, how do we work on this problem? Let's select a couple of problems to highlight today. First is, how much more energy can we store given certain weight, given volume of the batteries? So the Nobel Prize winning work, 2019, was built on 50 years ago of intercalation chemistry. You put the lithium in and out into a crystal structure in a very reversible way, causing very small disturbance to these materials, to this chemistry. But to store a lot more energy, you will need to consider new mechanisms that go beyond intercalation. This might include alloying. This might include plating and stripping. This includes complete chemical transformation or conversion right here. This is fundamentally very, very different from intercalation chemistry. It's so much harder to handle. So in my lab, past 19 years at Stanford, we took on this challenge and really start to look into new materials. They can store 10 times more charges compared to the intercalation chemistry. But they represent very, very big challenges. How do you do the alloy reaction? How do you do the conversion reactions? So let me show you by examples. Graphite is used in existing lithium ion. Based on intercalation of lithium between the graphene plane, this offers you 370 milliamp per gram of capacity. But if you could enable silicon to alloy with lithium or metallic lithium based on stripping and deposition mechanism, you have 10 times more charge storage capacity compared to graphite. This allows you to store a lot more energy. Similar on the positive electrode side, cathode. These are the current materials, lithium cobalt oxide, crystal structure, lithium manganese oxide spinel. And the lithium iron phosphate, these are the foundational materials enabling lithium ion batteries. And if you could go into conversion reaction that sulfur, lithium 2s, offer you about 10x of charge storage capacity. These are the materials make it possible with current lithium-ion battery energy density 250 watt per kilogram, all the way go up to maybe 1,000. We are talking about 4 times of energy density improvement. We are talking about for the same size of the batteries. Instead of 300 miles car you are driving, it can go to 1,000 miles. We are talking about the possibility of having electrical flight, at least on a continental flight. Across the ocean might be harder. Within 5-6 hours, this could all be electrified. So the impact could be really big if this possibility can be enabled. So let me come to the first example. When I joined the Stanford faculty in 2005, start to look into the battery problem. And silicon really come to my attention right away. It's 11 times of charge storage capacity of graphite, but its volume expansion is very, very big. It's 4 times. Once you put lithium in, it breaks nearly anything. And anything expands by 4 times in solid state. And this material, this chemistry, all these problems start to show up, and how to avoid breaking, and how do you build stable interface between each of these particles with organic electrolyte. Lithium alloy with silicon carries so much reduction power to reduce nearly any organic solvent in contact with this electrode. How do you build a stable interface? In 2008, we published the first paper really taking the approach of nanoscience, designing the materials with the size scale, with the surface and interface, which can handle the problem of volume expansion and breaking, and also instability of the interface. So this was my first paper published, and this has turned out to be the first paper really starting the whole research field of nanoscience design for the batteries. So we also developed tools as well to really try to understand what happened on these materials. What happened to this material? What happened on the interface? This is a transmission electron microscopy holder, and we built in this situ electrical biasing. You can pass in current through the materials, building a single nanowire batteries inside transmission electron microscope. This technique not only allows us to look at this nanowire structure, but also having this particle can be connected to these wires. And these nanostructures right here really offer small enough size for us to understand size dependence, breaking behavior. And let me share with you a few of these videos. And this is one of the videos of these nanowires, roughly with 200 nanometer in diameters. Once lithium coming in, the volume expansion is taking place. And this wire is coated with copper on the surface. And the copper is broken, but this nanowire is not. So below certain size, the solid state material do not break that easily. Let me share with you a broken, I don't know how do I play this video. Can somebody in the background and click on that video, then it's going to play. Somehow here I cannot click on. And you move the cursor to that picture. And then you click on that picture. Well, perhaps it doesn't work, but you need to trust me. There's a breaking behavior happening. It's good. It's a beautiful movie right here. And utilizing this video and transmission electron microscopy, we could identify what's the breaking materials design to avoid the breaking. So over the years, Okay. So this is showing the central particle right there. It's about 800 nanometer to start with. And this one, crystalline silicon core is shrinking. This forming lithium silicon alloy amorphous shell. Eventually, this particle is too big to really hold, to relax the stress, and it will be broken. Once it's broken, you are losing materials, you are losing your lithium storage materials, then the capacity is decay. So this battery's capacity decay is very, very fast, and based on this alloy mechanism. So using nanoscale design, we were able to, over the years, starting from nanowires, to relax the strain, to avoid the breaking. And we have been through about 12 generations of design because there are other problems right there. Interfacial stability, how do we handle that? There's another breakthrough concept is using double wall hollow structure that force silicon volume expansion towards the empty space inside. Then you can build stable solid electrolyte interface. So with all this understanding, we believe we are getting close to the final stage of solving all the problems related to silicon. And 2008, I founded my first startup company, Amprius, and really taking the idea from the lab and doing further development and manufacturing. Amprius is right now having the world's highest energy density batteries, supplying to the Airbus commercial drone. This commercial drone right here flying in 70,000 feet high and continues for 25 days, breaking the world record. In 2022, the company and the US part went for IPO and New York Stock Exchange. Now raising the capital, try to build further the largest scale manufacturing plant. This is the picture, the whole board of directors. We are in the bell ringing event. That was me right there. And so the challenges for manufacturing from commercial just started actually IPO. IPO is not the end of commercialization. It's the new beginning of the scale-up production. So after silicon, we need to look at lithium metal anode. This is based on deposition and stripping mechanism. Lithium metal anode is considered holy grail of the battery research. It gives you the ultimate energy density per weight. And in 1970s, that was even before I was born, scientists were trying to enable lithium metal, but it was not possible. That leads to the development of lithium-ion battery using intercalation instead of using metallic lithium anode. Based on the deposition and stripping mechanism, you take a lithium foil, you are going to react with organic electrolyte, generating this interfacial layer, but deposition cannot be guaranteed to be a very flat layer by layer deposition. You are causing surface curvature change. This break, this SCI layer, solid electrolyte interface, causing the hot spot, growing this filamental, we often call dendritic structure, lithium dendrite. This will go to the other side of the electrode, cause the battery shorting and catching fire. During stripping, there's no guarantee you strip from top to bottom. You must strip from the bottom because you take electrons away, you take lithium away, you lose control in stripping. And you can cause this dead lithium formation. So this has been half a century long old problem. How do we solve this? In 2017, my lab analyzing this and really narrow down to the root causes of the problem. One is high chemical reactivity of lithium. The other is plating and stripping cause such a big volume fluctuation. These two coupling together, one is the yin, the other is yang, really coupled together cause all the surrounding problems. Very, very hard to handle. So at Stanford in around 2015, when Steve Chu stepped down as a Secretary of Energy from that position, from Obama administration, we started to collaborate and we innovate for the first time the whole concept design of a hollow carbon with CD layer, guiding the deposition inside this hollow carbon instead of going everywhere. We also extend this concept further. Instead of using amorphous carbon, this can be graphitic carbon. This provides the mechanical resilience, guided deposition without causing mechanical breaking, further improve this concept. We also taking the graphene oxide, doing the molten lithium infusion between the graphene oxide layer, offer new type of host materials, hosting, deposition, and stripping without causing large volume fluctuation. And also how this graphene oxide is oriented, whether it's vertically, horizontally, or randomly on the electrode, causing the tortuous path to the different degree to guide the material's deposition. This host concept design turned out to be one of the most important concepts to enable the deposition and stripping chemistry on lithium, on sodium, potassium, and also on other metallic anode. And the second one is with my colleague, Professor Zhenan Bao and Jian Chen, is how do we borrow all this idea in organic chemistry, organic chemical reaction to guide the electrolyte design, guiding the solvent design, putting in, for example, the effect of stereo effect, electronic effect right there by adding fluorine atoms, and also fine-tuning the symmetry of the molecule, the dipole moment, to really now systematically design the electrolyte, having very exciting breakthrough in these areas. Also equally important is the tool development. In 2017, the Nobel Prize was given to cryogenic electron microscopy to solve the protein, solve the biomolecule structure. We actually borrowed the cryo-EM technique and utilized that for the first time to look at very fragile battery materials and really guided the development of the energy material using cryo-EM. These other new tools. We keep learning and borrow that and put it into the battery research field. So this is still ongoing. Now I want to share with you the second big problem we need to solve. And high energy battery is for mobility, but for long duration, stationary energy storage, for solar and wind electricity integration into the grid. This is a multi-time scale problem. For electricity grid right here, you need it to be stable, the voltage needs to be stable, frequency needs to be stable, and you need to have minute to minute storage, input and output to stabilize the grid. You also need to carry all the way to seasonal storage. This is really tough problem. You want to have very safe electrochemistry, never catching fire. You want to have very long lifetime lasting for 30 years, 30,000 cycles. Then you can do 3 storage cycles per day, continuously for the next 30 years. You want it to be very low cost. Then what's the chemistry available for you to do that? Let's revisit aqueous electrochemistry. We know electrochemistry originated from aqueous solution. In 30 years, when we move into lithium-ion batteries, that's the organic solvent-based battery. Before that, it was always aqueous electrochemistry. Aqueous offer you really extreme safety, no catching fire. But what's the longest lifetime chemistry available? We started to look into nickel hydroxide, nickel oxide hydroxide. This is well known for nickel metal hydride, nickel cadmium batteries, and it can run for a very long time, this cathode chemistry. Then we asked the question, if we could take this cathode chemistry and utilize the anode chemistry, that's hydrogen become water, that's half of the fuel cell, and combine these two together, we can construct new type of full battery reaction. Now we call nickel hydrogen gas batteries. So as soon as invented this, we discover NASA in the United States has been using these batteries for Hubble telescope, for International Space Station, out there in the outer space for 30 years already. It's so reliable. This is the proving point, reliability, lifetime of this chemistry is very robust. However, the biggest problem is the cost is too high for NASA technology. They use platinum as catalyst. Now we change to nickel, moly, cobalt. This again, come back to the topic today, catalysis. these catalysts are so important right here to help reducing the cost. So we construct this chemistry, for example, running for 10,000 cycles right there without decay. This is very robust chemistry. And not only that, the nickel one, we also innovate using other metal elements with a 10x low cost. For example, manganese, Mn. And we invented for the first time of a manganese hydrogen gas batteries based on cathode is manganese 2+. Deposition from manganese dioxide solid. Anode is hydrogen become proton back and forth. This beautifully generate very long lifetime manganese hydrogen gas batteries. So 4 years ago, I spun out another company called Inovanio. Inovanio right now is taking this technology, designing it into this real product right here. For example, this one battery cell, the diameter is about 12 centimeters, like this big in diameter. The length is 1.8 meters long. One battery cell stores 3 kilowatt-hour electricity. We are building this unit right now, also building this rack for the largest scale energy storage. Let me highlight the very wide operation temperature window. This is a chemistry based on potassium hydroxide solution. It's a freezing point. It's minus 42 degrees Celsius. So this chemistry can extend from minus 40 to plus 60, working so well. This is what lithium-ion batteries cannot offer. Lithium like to operate at room temperature. Very low is bad, very high also very bad. So, but this is the chemistry now, nickel hydrogen gas battery we can offer, and for the long duration energy storage. So at the end of my talk, let me share with you a very exciting news. 1 month ago, US Department of Energy announcing a DOE Energy Innovation Hub. This is $62.5 million energy hub. I serve as the director of this hub. We just got awarded. This is the hub. We try to look into what would be happening in the next 30 years. We want to look for 10x cost reduction. Extreme safety of the battery chemistry can allow us to go to 200 terawatt-hour scale, billions of tons of materials. There's very few choices right there. We need to look at aqueous chemistry. We need to look at very low cost, redox chemistry, zinc, manganese, iron, construct new type of battery chemistry for storing large quantity of electricity for seasonal energy storage. So organize a team consists of these 32 scientists right here, coming from 15 institutions. This is led by Stanford University, and I serve as a director. Linda Nassar serves as our chief scientist. Steve Chu is our advisory council chair. We have really very talented folks as a team working together for the next 5 years, try to enable new type of electrochemistry for stationary storage. Let me summarize my talk. These are the guiding challenges has been guiding my research lab in the past 20 years to innovate in these areas. I give you the example of high energy density batteries and one example on grid-scale energy storage. There's a lot more to come to enable the circularity, extreme safety, ultra-fast charging. With that, let me end my talk by thanking the whole research group and Department of Energy for the long-term support. Let me say congratulations to Professor Li Yadong and Zhang Tao again for your Future Science Prize on catalysis. This is the highlight of the whole chemistry. Thank you very much for your attention.
So thank you very much for the wonderful and exciting developments showing us how not only fundamental basic science, but all the translation. And also congratulations on the consortium. So thank you very much. So let's move on to the third lecture. So the third speaker is Professor Peng Chen, the Peter J.W. Debye Professor of Chemistry from Cornell University. And he's going to tell us something different But this is the good thing about chemistry, is really a central science covering all aspects. Single molecule chemistry, again, very important topic. Professor Chan, please.
Thank you, Vivian, for having me here. And we just heard two beautiful talks, how you can use chemistry to make very important molecules or very important materials. So what I'm going to tell you in the next about 25 minutes is how we can study chemical processes down to single molecule level. And in three different areas. Now, this is all start with the development of optical microscopy over the many years. We probably have seen antique microscopes maybe existing in this particular museum, but with the development of the optical microscopy, now one can purchase such instruments and put into your lab bench and to do or to study fundamental chemistry. One can see individual bacterium cells. One can also see catalyst particles. If you detect the fluorescence, one can see individual molecules, or maybe individual molecules in cells. Now, my lab has been using these technical capabilities of studying fundamental chemical processes. So what I will show you today is three short stories about looking at catalysis on nanoparticles, looking at polymerization reactions, and also protein complexes on the surface of bacterial cells. We're talking about catalysis again. I probably do not have to tell you the importance. Now, this year's, of course, physical science prize laureates are Professor Zhang Tao and Professor Li Yadong for their, I cannot see that, seminal contributions in single atom catalysis, where you use individual atoms as catalysts. I also want to point out that another class of catalysts one often use are nanoparticle catalysts. Now, these nanoparticle catalysts, a salient feature of them is their intrinsic heterogeneity. Now, if you look at a population of nanoparticle catalysts, they always have different sizes, different shapes. One can wonder, what are their catalytic activity differences? Even on a single particle catalyst, it can have many different surface sites. For example, in this bimetallic palladium gold particle, it can have monometallic sites. It can also have bimetallic sites at the interfaces. Can one directly visualize which sites are more active than the others? Furthermore, if you apply these nanoparticles in catalysis, their structure or their morphology often change during a course of a chemical reaction. That will give you time-dependent catalytic activity that is typically not known. Can we visualize or understand these time-dependent catalytic properties at the fundamental level? Now, to study these processes or to answer these fundamental questions, one really needs to study catalysis of individual nanoparticles in real time and spatially resolved. So a number of years ago, my former postdoc, Wei Ling, did an experiment so that he can utilize fluorescence signals of individual molecules to monitor catalysis on individual nanoparticles, which are made of gold. So shown here in this picture that the bright spot is the fluorescence signal of a single reaction product sitting on a single particle catalyst. I will show you a movie here. The flickering is noise. But if you focus your eyesight at the middle, what you see here is flashes. It's like in the dark sky, you have flashing stars. Now, each flash is one catalytic reaction catalyzed by one particle. One can plot out this fluorescence intensity as a function of time, and you will see these so-called off and on telegram signals. Each intensity jump marks a catalytic product formation event, and each intensity drop marks a product desorption from the catalyst surface and a go away in the solution. Now, each off-on and on cycle is a single catalytic turnover. Now, one can even zoom in into this image further and can localize this molecular position with nanometer precision, which is the basis of another Nobel Prize in super-resolved fluorescence microscopy. So what we have here is now a single reaction resolution and looking at single nanopart catalysis in real time. So one of the first things we learned by looking at the data is that if you look at the catalytic activity for a single gold nanometer particle as a function of time, this activity fluctuates over time, even though every single experimentally controllable condition is kept constant. So what you see here is really the underlying structure dynamics that I alluded to earlier. During catalysis, the surface atoms of the nanoparticle catalyst can rearrange. When the surface structure changes, activity changes. So what you see here is really the functional manifestation of the underlying structure dynamics. Now, since we can resolve every single reaction and also determine its location precisely with nanometer precision, now we can look at, for example, a gold nanoplate catalyst and spatially determine where every single reaction occurs. Now, each dot on this plot is a single reaction. But now we can see reactions happening on corners, along the edges, on top of the facets. One can now directly visualize that the corner has most activity, followed by the edge regions, followed by facet regions. So you have a visualization of a site-specific activity on an individual catalyst. This is done by a former graduate student, Nesha, and also a former postdoc, Xiaochun. Now, all of these examples that I've given are built on the fact that we're detecting fluorescent signals of a catalytic reaction product. What about chemical reactions that do not have any fluorescent species? Can we do similar imaging down to some similar level? So my former postdoc, Xianwen, developed a technique, we call it COMPETES, that stands for a little mouthful term here. So the fundamental idea is that if I have a catalyst that can catalyze fluorogenic reactions where the product is fluorescent, I can map this fluorogenic reaction on a single particle with nanometer precision. Now, if I have another reaction, neither the reactant nor the product is fluorescent, but this reaction happens on the same particle surface and where the reactant will compete for the catalyst surface sites. So once you introduce this competing reaction, this original fluorogenic reaction rate will suppress at all the possible places on the same particle. And that suppression can be mapped at the same nanometer resolution, and that suppression also tells you about this non-fluorescent reaction. So we implement this to look at photocatalysis on bismuth vanadate particles. We can map a fluorogenic reaction on this particle with individual molecule nanometer resolution. He can count the number of molecules at all the possible places. Now we introduce our competing reaction. I'm not telling you what the exact reaction here, but this competing reaction is non-fluorescent. Now you see everywhere this original fluorogenic reaction is suppressed. Then you take a difference of these two images. Turn out in the inverse space, now this image is directly proportional to this adsorption equilibrium constant. of this original non-fluorescent reaction. So what you see here is a visualization of an adsorption affinity of a non-fluorescent reaction, and shown here, adsorbs stronger on this top facet, followed by this lateral facet, and followed by these corner regions. My second story, I want to use similar methods of looking at polymerization reactions. Now, perhaps I don't need to convince anyone synthetic polymers are important in our daily lives. You might have used any one of these things. Now, synthetic polymers are important to make. Of course, they're equally important to study. Now, one of the challenges about the synthetic polymers to study is their, again, heterogeneity. If you have long chain polymers, different chains often have different lengths. If you have copolymers, the monomer arrangements differ from one chain to another. Now, fundamentally, it's really due to the fact when the individual polymers grow in the synthesis process, they grow at different rates, and different monomers are also incorporated unequally. Now, to understand these things, I'm a physical chemist. I thought perhaps we should track single polymer growth in real time, now preferably even at single monomer resolution. So that's what we set out to do. My former postdoc Trimming, student Kerry, another postdoc Suso, developed this technique utilizing magnetic tweezers, where we tether a single polymer between a surface and the magnetic particle. We use external magnet to attract the particle to stretch the polymer upwards. So now if you have a catalyst here, they can catalyze the insertion of the monomers, the polymer will grow, and this particle will move upwards in Z. So by tracking the position of the particle in Z, we can track the real-time extension increase, which means the real-time polymerization reaction of a single chain. Now, the underlying chemistry, again, is another Nobel Prize chemistry that is called ring opening metathesis polymerization. We have a ruthenium catalyst here. The other end is linked to the surface. Catalyst is immobilized on the magnetic particle. We flow in the cyclic olefin, coordinates ruthenium, form a ring opens, and the monomer inserted. You repeat the cycle, the polymer grows. Now, to track this particle in Z, we shine light from the top, we collection transmission images from the bottom. Optical microscopy can have these diffraction patterns when this particle is away from the focal plane. Now, when the particle is closer to the focal plane, it forms different diffraction patterns. So by analyzing the pattern, we immediately know the Z position. Now, I'll show you a movie. If the movie plays, the movie is not playing. Can someone click that picture again? Let me try it again. Okay, I can't do anything. So imagine in that movie, you have a particle, you have a polymer grows towards you, and then the ring pattern will just grow bigger and bigger. Is it really playing now or not? Confusing now? All right, by analyzing this movie, we can look at how a polymer extension increases as a function time. What we discovered unexpectedly now is that the polymer extension does not grow continuously, but have these long wait periods followed by instantaneous jumps that comes from this formation of this non-equilibrium entanglements that form probabilistically and then unravel also probabilistically, and turn out these non-equilibrium conformational entanglements was never known before and also controls the polymerization kinetics. So this magnetic tweezer technique was great for us to follow individual polymer in real time, but did have one limitation, that we could not resolve every single monomer being added in. We thought maybe we can come back to fluorescence microscopy. So my former postdoc Xiang Chen, Rocky, and Shenwen developed another technique. We call it creates, that stands for this particular term. What we have here, again, is a surface grafted polymerization reaction where the polymer can grow by adding monomers. But this polymerization reaction initially carries no fluorescent signal. But now we have another reaction that happens on the monomer that is tagged with a caged fluorophore. Now, since the monomer of the fluorophore is caged, it does not have fluorescence, so it can be supplied with high concentration, so the polymerization reaction can continue or go on. But now we can zip of the laser light, time it in a proper way. Once the monomer is added in the polymer, we uncage the monomer, release the fluorescence. By detecting the fluorescent signal, we can see every single monomer to come in. So by coupling two different reactions, we should be able to monitor every single monomer being added into a growing polymer chain. So we immobilize the catalyst on a silica particle. That the catalyst is also fluorophore labeled. So here is the scanning electron microscopy of the marker particle. We do fluorescence imaging, and we can localize the catalyst is here in this dark image. We can supply now our caged fluorophore monomer A that carries a green color and do our uncaging fluorescence detection. Now I can see every single monomer being coming in a sequence as a function of time. Now for every single monomer we detect, we can also localize its position, and now you can see every single monomer is landed on a single catalyst. So what we have here now is a single polymer growth with single monomer resolution. Now we can use two different types of monomers, A and B, that carries green color or yellow color. By visualizing every single A, every single B being incorporated onto a single catalyst, the landing on top of each other, now we can plot out the A and B as a function of time. So now you can see B monomer, A, B. So not only we can see every monomer coming in, we can also determine the exact microscopic sequence of a synthetic copolymer. Of course, this is just one. We can look at many synthetic copolymers. We can microscopically determine the exact sequence of a single polymer chain. And turn out these sequences shows a blocky pattern. This is supposed to be blocky, not blacky. Now, we think now this is a step towards ultimately, maybe we can do sequence function correlations to study synthetic copolymers. Now, in the remaining minutes, I will show you a topic that goes into biology, looking at bacterial proteins inside a cell. Now, a bacteria is a little unfortunate compared to us. They often live in very, very harsh environments. They could be surrounded by heavy metals, antibiotics, or detergents. All of these molecules can be toxic and kill the bacteria. Bacteria, of course, is also smart. It has developed many mechanisms to defend against such toxic chemicals. One of the most general mechanisms is using efflux, using protein complexes that have an inner membrane pump, outer membrane protein pore, and also periplasmic adapter protein that can pump the toxic chemical, for example, copper or silver, out of cell so that this cell can survive. Now, if you look at these structures at the cartoon level, these complexes link the inner membrane and outer membrane through the cell wall together, potentially form very rigid linkages that make this cell envelope or the periplasmic space more rigid. And that potentially can risk this periplasmic plasticity that was known to be important for a gram-negative bacteria such as E. coli that I've shown here. Now, people always wondered, maybe such multi-component complexes do not have to be assembled all the time. They can undergo dynamic disassembly into its pieces and only form the assembly when they are needed to pump out toxic metals like that. So my former postdoc Tae-Yan and student Ace, decided to take a look at this, what is true inside a living cell. So the strategy is very simple. If we can tag this inner membrane protein with a fluorescent probe and image and track its motion inside the cell, this should be a stationary object because linking the cell envelope, and this would be a much more mobile object moving around along the membrane. Indeed the case, we can track these individual proteins in the cell, for example, shown here, by taking snapshots of images. We can track its motions. We can overlay many of these motions together. Now you can see sort of slow stationary objects. You can also see very fast moving ones that corresponding to the mobile or the stationary objects. One can also determine that in the absence of this toxic chemical, these two states exist in 50-50% ratio. But now if you put this toxic chemical in the surrounding and this equilibrium shift to the right, so you can assemble these protein complexes to pump the metal out of the cell. It was great for us to watch how these proteins behave inside the cell and learn about the properties. We thought, can we actually do something to the cell and manipulate this protein complex? So the idea was, perhaps we can put this individual E. coli cells into a taped fluidic channel. One end is bigger than the other. By squeezing this bacteria into this channel, we can deform it. Now, if these complexes make linkages on the cell envelope, by deforming the cell, we might be able to disrupt the assembly and compromise its function. You may wonder, why should one do this type of a squeezing into a tight space in the first place? It turned out, in nature, for example, in bone tissues, bacterial cells can squeeze into these tight spaces to escape from macrophages. Bacteria can also live in aquatic environment that is surrounded by hydrostatic compression. If they adhere to the surface, they also have adhesion forces. If you have a solution flow, you also have shear forces. So these mechanical forces happening in nature actually can also be applied or present in this device, but now in a way that we can control it precisely. So we collaborated with a mechanical engineer, my former colleague Chris Hernandez, and her student Melanie, and also my former student Lauren, to look at this. My collaborators made these devices. They have microfluidic channels. One end is bigger than the other. Now individual bacteria can be squeezed in. Now Lauren can come in to do single molecule microscopy and tracking the motions of every single protein inside a single cell. Indeed, we can show by increasing the solution pressure difference between the upstream and downstream with increasing delta P, we can indeed disrupt the complex of this assembly and make them into pieces, and then compromises the bacteria's defense against toxic chemicals. So hopefully, I have given you 3 examples that give you a little flavor how one can use fundamental microscopy to learning about fundamental chemical processes in a variety of different topics. I want to thank you for your attention. I also want to thank my former group members and also the current group that did all the work. Thank you.
So thank you very much. Very enlightening talk about single molecule chemistry and how one can really follow the individual molecules and all the reaction and processes. So the next and the final keynote speaker this morning is Professor Jinyao Tang, and he's a professor at the University of Hong Kong, and he will tell us about active phase transition and new material on move. So, Jinyao, please.
Okay. Thank you very much. It's my great pleasure and honor to be here to share some of my work. And firstly, it's congratulations to Professor Zhang Tao and Professor Li Yadong for their works on catalysis. So I will be your doorkeepers to prevent you from the lunch. Sorry for that. But hopefully for the next 20 minutes or so, I would like to introduce you a new field, which I borrowed the word from Richard Feynman. It's a field that little has been done, but in principle, enormous can be done. So that is a new area, that is a new material on move. Yeah, so if we actually looking around us, so if you're having a good eyes, so you're seeing these kind of behaviors, right? You see shattering of the glass and diffusions, rotting and rustering. And so we call it this as the arrow of time, so the entropies. So things is actually changing from an order state to more or less disorder state. So that is the nature of our universe. So on the other hand, if we are thinking more carefully about this, so this is actually nature of the more or less dead world, so whenever it's not really living. So if you're looking more on the other side, which is livings, like bacteria or something, right? So these things are different. So they actually starting from a very disorder state to a more or less order state, for example, this kind of self-assemblies from the very beginnings. So what looks like there is some kind of gap between the life and death. So there must be some kind of missing part in between of this. So what kind of missing part is there can bridge these two areas, because after all, we're living in the same world governed by the physics. So one thing actually very easy to think about is motion, right? So at the very beginnings of science, people are thinking like something that moves, that is life. Something that is stationary, stay there, so that is dead things. Right? For example, these kind of moving bacteria, so this is swimming around, you can see them very easily. On the other side, if you're having tiny particles, you see they actually also moves, but it also moves in a very different ways. So these ways, Albert Einstein told us, because they're actually bounced by the nearby molecules or gases in the solutions. So they're constantly jiggling around. So you can very quickly distinguish this kind of motions versus this kind of motions. They are different, okay, without doing any mathematics. But is there any way we can bridge this one, finding a gap between that or bridge between that? So this is a little bit about 20 years ago, people start to find some kind of inorganic particles. So this inorganic particle, very simple. It's gold and the platinum particles. And you stick them together, and you're putting inside the hydrogen peroxide solutions, which we actually use it to disinfectants. So you put there, I can see these particles start to swim. Obviously, they're just like this, but this has nothing to do with the living things. They're not life. So it looks like there is a missing parts we find bridging the life and death already. So for the, my lab, for the last, a few years, we actually working on this field. It's, we call it a swimming colloid or active colloid. It's essentially, it's a catalyst. But instead of doing the catalyst really doing good things, like has a product, we're having the catalytic interactions or reactions on it. For example, like we're shooting light particularly. We were shooting light onto our particles. They're starting doing some kind of surface chemistry. When they actually do, this surface chemistry will propel these particles start to swim, right? So different kind of swimming. There could be phototactic, and that means the drives or chasing the light, or they could be photochemically, or they're just chasing different kind of colors, or different kind of polarizations, or different kind of phase of the material of the light. Either ways, these are our new material on move. But like when people are asking, like, what you guys are doing here, like we're trying to say is we're trying to build some nano robot. Eventually, we're going to use it for like kill cancers or something like that. But today I'm going to say something else. Is maybe we're actually using this as a new building blocks, fundamentally, for materials. Because if you're thinking about new materials, like what kind of materials you're like sitting on, you're facing on, it's just made by atoms, whatever the atom it is, right? So this, no matter how sophisticated it is, it's an aggregate. It's just a bunch of the atoms stick together, so maybe some kind of molecules. And they arranged in a different ways, could be the crystals or amorphous or gels. But in either ways, these materials is dead, right? So they're not doing any kind of non-equilibrium things. They're actually sitting at the bottom of the energies. However, if you're looking differently, so crossing these boundaries, like if we have some kind of colloids, some kind of particles, they start to move, they could self-assembled into some kind of intrinsic, complicated structures. But we never think this as a material. We're never using them in that ways. But like in nature, there are many of them. So for example, there's motor proteins, there are bacteria, there are cells, like the birds, also yourself. It's a active things, but it's not a material. Or maybe like it could be a material, right? But either ways, once we cross these boundaries, we're starting from the equilibrium system to non-equilibrium systems, we can build something different. If you have a static parts, right, so like here, so we're going to have the static assemblies. Well, we can build them using the very classical thermodynamics. But if you introduce something else, like the moving parts, something can start to move, maybe we can build something more sophisticated, right? So something more intrinsically different. From a thermodynamic point of view, like assemblies, we, as our materials, is actually over here, right? So we are actually equilibrium at the energy landscape. It's somewhere here or somewhere here. So either global minimum or locally minimum. So I call it equilibrium materials, whatever, the wood or something dead. So if you are clever enough doing some chemistry on that, for example, we can have some kind of transition from one equilibrium state to another equilibrium state. For example, like Professor Vivian Yan's group, they're actually developing this kind of photochromic materials. So you're shooting light on it, so it's switching from one to another. So, but either way, so they're actually sitting on the bottom of the energy landscape. So we call it responsive materials or functional materials. But if you look closer, like there's large areas, like in the energy landscape, we don't know what their property is because they are transient, they're not stable, so you cannot access to it. But however, if we actually having some kind of dissipation reactions, some kind of interaction on it, maybe we can stabilize these active species, so make them into a useful material. So that is actually like my goals of comparing like traditional materials versus active. Just give you examples, very simple examples, like when we're actually learning basic chemistries, like it's like this. So if you're having two kind of particles, like for example A and B, it could be molecules, it could be anything, right? So there is two things could happen. One, these two things mix, so we call it miscibles. Another thing is it could be just oil and water, so they could be immiscible. They separate each other. So why this is the case? Because if you have A and B, they are very like each other, so their interaction is equal to each other's. So entropy is going to drop in, so you're starting getting these mixtures. However, if you have the particles A wants to stick with another particle A instead of B, so they're going to be phase separated. So they're basically separated from each other's, becomes immiscibles. So by interaction difference, so you're driving these separations. Chemistry-wise, like we actually could do this in the experiment. So we're actually inspired by the dye-sensitized solar cells invented by micrograssels. So this is a solar cell. So this is what solar cell really does. You have the titanium electrodes, you have some platinum electrodes. So in between, there is some photo redox shuttles and some dyes. When the light is shooting on it, so electron is transferred through this channels from the electrode to the dyes, to the redox shuttles, to the titanium, and then go to the external circuit. So that is dye-sensitized solar cells. For us, we don't have that. We just have particles, and we load the dye onto the particles. So that means there is no electrode, there is no external circuit, so there is no energy, I'm sorry. So we wasted the energies, but there is still catalytically doing the reaction. So this chemical reactions is, so the electron goes through here, but they basically wasted. So we're wasting a lot of energies, but also we can generate some chemical reactions on the surface. This chemical reaction on the surface is going to generate a chemical potential difference, or the chemical gradient on the surface. We said the electrode is polarized. So thinking about if you're having particles nearby, because this is a concentration difference, so they're going to face this kind of concentration difference and generate some kind of sporadic flow. So in this case, it could be repel or attraction. So in this particular case, they could attract each other. So essentially, we could have particles, and you can excite it with light. So transform the passive particles into active particles. Fortunately, we can actually doing this in a more spectrum selective way. So you can use different colors to do that. So you can actually getting the passive to active, or passive to active to active interactions. Some is stronger, some is weaker. So we're actually doing the experiment, actually measuring these interactions. So for example, if you have a red particles, so red particle means they actually absorb the blue light. So when they do, so the interactions between these two particles getting stronger and stronger with the intensity of the light getting stronger, while the blue particle doesn't absorb the blue, so it doesn't do that, versus the blue particle absorbs the red, so something like that. So again, kicking the physical chemistries. So if you're thinking about the mixtures to the separations, so this is called the phase transitions. For example, you have the well-mixed system, and you could think about this phase diagrams. If you cool it down or heat it up, you are transferring from the one phase to another phase. So you actually could get this phase separations. But that is by changing the temperatures. So in our case, we're actually having a chemical reactions, because over here you can have this temperature over here, and this is a difference between the interaction, right? So which can be controlled by the light. So if this numbers is going greater than 2, so they're going to phase separate. So we can do that, okay? We have the interactions. So this is the axis is light intensities. Across these boundaries, you're starting to get this phase separations. So again, we can use a blue light to excite the red particles, or using red light to excite the blue particles. So essentially, over here, you can see this phase separations from the blue light gradually increases, goes degraded to the red light. So they're phase separated. They're both phase separated, but the phase separation is different. In this case, the red particle is inside, versus here is blue particle is inside. If you're doing this a little bit more, so for example, you can have this primary color, so the red, the blue, and yellow. So you can have this phase separations in a more color-sensitive ways. So you shooting light on it, and you move the boundaries into the phase separation regions. So by shooting different colors of the light, so you're starting to get different kind of phase separations, right? So color-sensitive ways. So a little bit more. So if you put in more of these particles, they cannot do that easily, but like they're going to like phase separate it in a little bit more like this ways. So you're shooting light on it with a pattern on it, because as a primary color, you put them together, it's a black. But when you're actually shooting light, they phase separate it, they're showing colors already, right? So just like one thing is coming out. So if you're shooting the red on it, so they're showing red. If you're shooting the green, they're showing green. So you can put in a different kind of patterns on it. Obviously, that's going to follow whatever the patterns you get it. So this is actually the same ways of the squid actually changing colors to the environment. So when these squid actually face, okay, whatever the environment color is, so they're going to try to push their pigment on the surface, so that is going to change the appearance of that. And remember, this phase separations is dynamic, so there's not thermodynamic equilibrium, so that means it's transient. You can actually change in them into whatever these patterns could be, right? So you can change from one to another and to another, continue going, right? So this is truly dynamic in the sense. Right, so this is one thing, like, because like when we're actually having these particles, they're pretty much random, they're chaotic, they're not really forming some kind of order structures, so we call it the liquid or colloidal liquid. So we can do it in the solid state as well. So like, for example, they form some kind of more closed packed one. So in the particles in the world, like we can have this one. So this is a silica particles, they actually forms a closed packed regions, like assemblies. This is opal. Like from a jewelry point of view, this is interesting, but from a scientific point of view, it's not very interesting because this is only thing they actually forms. But if you look at the atoms in chemistries, so they could be different because chemistries, we know the atoms have a different kind of orbitals, electrons. So electrons could be spherically symmetrical, could be not spherically symmetrical, right? So because they are not spherically symmetrical, you could have all kind of crystal systems, which is more varieties, right? So there can be more functions to that. Can we actually build our active colloids in their more asymmetrical ways? So actually very simple as well. So if we have particles like this, similarly, previously we're actually shooting, let's say for the red particles, we're shooting blue light on it, but this time we're actually shooting red light on it over here. So the red light shooting on it, it's not going to absorb very strong, so that's going to pass through, but because of the reflective index, it's going to focus on a tiny spot on the particles, but it's going to do a little bit of excitation, so there's still some photochemical reactions, catalytic reaction on it. So for example, it's going to be having a reaction over here, and this particle becomes like asymmetrical particle. So if you're just shooting like that, so this particle starts to move. But if you're shooting light from the both directions, it's going to be more like a p orbitals already, right? And we can see that, okay, we're shooting light on the both sides, so you can see this, okay, a little bit attractions and the repulsions, but this really looks like a p orbitals. So we can try to massage this p orbitals, whatever the shape we want to. So you can imagine if you have many of these particles around, and you're shooting light on it, on both sides, so they're going to arrange in a certain ways, right? So this is actually what we see. Very simple. You have like a lot of particles and shooting light on it, and they're actually arranged into this linear shape of that. So this is a little bit more like a p orbitals. And the good thing about this is, because this is just like shooting light on it, so we can have s, p, and d, f orbitals. So if you're shooting light from whatever the direction you want, so you could have all kind of interactions as you want. Some of them is like the ps orbitals. Sometimes it's not really have the symmetries available. for example, over here, so this is not whatever it is, right? So like it's not a p orbitals anymore. But either ways, we can have these kind of interactions on it, and these interactions is going to lead to a kind of assemblies. So predictably, you can just like using a very simple a statistical thermodynamics, you know it's going to assemble in these different structures. Because in two-dimensional space, there are actually 5 possible lattices, could be possible arranged. In our ways, it's going to be like these 5. So you're shooting light on it, and they're forming all these 5 lattices, possibly, on the 2D space. Right? So what we can do about this? So like at this moment, they're not doing much, right? So we have this dynamic particles, or assembly crystals, and these dynamic crystals, you can shooting light, let's say a laser on it, so it's going to diffract the laser's beam. So, but because it's a dynamic crystal or active crystal, so you can use it, one light, or basically a light around it, to control another beam of light. So it's just like a circuit, right? So like in the transistors, you have the electricities to control another electricities. So we can use it to control the light from another light. Right? So it's not very quick because the particle-wise, it's relatively big. But like on like every second, you can switch it a few times, something like that. Right? So that is the active crystals. And because we actually could make this p orbitals, d orbitals, whatever the orbital is, and massage like it's changing the shape of the orbitals. So you can actually getting a little bit about the colloidal chemistries on that, right? So they can form this kind of polymers, so there's kind of 2 particles around, and you can have this crystal lattices and the forms just by changing the light intensities, light frequencies, and light directions. So without like much, I think it's that's pretty much I want to talk about. But our idea is, so switching from the building blocks, which is very like simple thermodynamically equilibrium building blocks, to active building blocks, we may be able to access some active clusters and phases, which is not available, maybe some properties that could be possible for us. And for example, which I don't have time to actually mention, is some of the properties, assemblies, that is not possible for thermodynamic equilibrium system, for example, this swarming systems, or intelligence system, for example, yourself, self-polarizations, and we also could make it into the molecular scales. Hopefully next time I can share you about this. So making these all dynamic assemblies in real materials. Without too much, like I think it's, we expanded from the equilibrium material systems to a more and more active systems. And I think it's, we're starting with like very finite known to like infinite unknown systems. Okay, so that is all. I want to make thank you to my groups and the funding support, and also thank you very much for your time and attention.
Thank you so much, Professor. Please stay with us. Could you please come forward, because we are going to have another session. We'll have your participation as well. And our experts just explored topics such as the acid catalyst, single molecule chemistry, and active phase transition, highlighting the potential of chemistry to address global challenges and inspire future scientific advancement. And we are very happy to have a panel discussion coming up next. For the panel discussion, we'll delve into the role of chemistry as a central science that connects various disciplines, driving innovation, advancing interdisciplinary research. We are very honored to introduce our moderator, Professor Vivian Winghua Yam. And our panelists, including Professor Chen Peng. Professor Chen, please. Professor Cui Yi. Professor Benjamin List. And of course, on the stage already, Professor Tang Jingyao. So I may pass the time to our moderator. Thank you.
So thank you very much. So I would like to thank all the speakers for all the wonderful and fantastic talk, giving us the flavor of how chemistry will be able to play a key role in changing our world and contributing to a lot of global challenges. So today we'll have a discussion. So thank you for also coming for this panel discussion. Today we'll talk about, because the title of this section is really chemistry is the central science, and I guess all chemists would agree to that. So maybe can you share with us, maybe Ben first, on how you think of chemistry in really, do you think it's really a central science? And how would it contribute towards really meeting all the global challenges? You already show us catalysis is really one of the very important things that changed the world, and so please.
So, well, I like to start by sharing with you how I got interested in chemistry, because it was a deep misunderstanding. I was 11 years old, and I kind of knew already the world is made up of atoms and molecules and matter and so on. And so I had the impression that chemists understand everything, literally the whole universe. And so I was drawn to this because I had these philosophical questions on my mind. So how, why are we here? Where are we going? And so on. And why is there something and not nothing? And then when I became a chemist, I more and more realized, unfortunately, these questions will not be provided, or the answers to these questions will not be provided by chemistry. But I was already hooked, and chemistry is the central science, as you said. It's like so incredibly relevant for our life. I think that's really unsurpassed by any other human cultural activity that we have developed over the last few thousand years or so. And while I'm like a fundamental researcher, I like fundamental science, and I'm happy that I share this interest with you here in Hong Kong and in China as a whole. Other countries are moving more to applied science. During the pandemic, actually, I realized how impactful it is if we look at actually real problems like batteries or something like that. Like, how can we contribute to our life on this planet? And I'm very enthusiastic now about using our research in fundamental science and to solve actual real-life problems.
Yeah, thank you. So Yi, how would you sort of give us a flavor?
Can you hear me? Sounds good. I think, just to remind everybody, even though I'm in material science department, I have my undergraduate degree, PhD degree, and postdoc all in chemistry. So I'm fundamentally a chemist. Maybe one way to think about resonate what Ben just said. When you look at chemistry, it's the foundation. Chemistry can be so important for energy, so important for life, important for huge amount of industry areas. So it's really foundational. Fundamentally, chemistry really offers first the tool to make things, produce things. If you cannot produce things, you just cannot study that. You cannot use it. So that's so important. And making things, synthesizing things. And also chemistry is dealing with complex systems oftentimes. The real life is fundamentally complicated. And chemistry is dealing with that. I mean, this is common, it's probably refer back to physics. Physicists want to study simple systems. And chemistry is dealing with a lot more complex systems. It's just no surprise chemistry is essential science to everything we do.
Yeah, thank you. Yeah, chemistry really connects between biology, right, physics, engineering, and everything sort of like you can think of. And so, Peng, can you say something on that?
So I consider, I guess, chemistry as a central science as sort of how it interfaces with other disciplines, perhaps in two directions. So I say one direction, chemistry have benefited from the advances of other disciplines. In my own research, microscopy, which is mainly perhaps advanced in the physics field, they have provided tools that we can now looking at fundamental chemical processes at a deeper level. Now, electron microscopy, synchrotrons are all techniques coming from, let's say, mainly other disciplines. Now, the other direction is chemistry, of course, provides a lot of solutions to other disciplines, perhaps understandings. Now, biology is very complex. At the bottom of the biology is actually chemical processes make biology fantastically complex. And I think understanding the chemical processes provides insights into biology, and I think this is another feature of chemistry being a central science discipline.
Yeah, thank you. So particularly your work looking at single molecule, right? Because what we see usually is a whole ensemble of molecules. It's really a time average thing, even the kinetics, right? But you're looking at individual ones that will be behaving quite differently. So it's interesting in a way. So Jin Yao?
Oh, thank you. Yeah, I just want to ask others in the audience to think about what chemist really is. So chemist is really coming from the alchemist, right? So alchemist. So what do you think about the alchemist or actually other field? So if we are actually thinking about the physicists, they're actually doing equations, those kind of things. As mathematicians, they're going to do very sophisticated things. And chemist is a doer, right? So it's actually doing, our hands get dirty, and we're actually getting things materialized. And the other side is because chemistry is really make things works. So this is also why I think at this moment, a lot of this other area people actually get in and getting Nobel Prize for chemistries with physicists, with mathematicians at this moment. But it's in one way we're actually thinking as a chemist is it's sad other people comes in, and other ways actually this is a good area everybody wants to get in. Thank you.
Yeah, thank you. So actually there's no sharp demarcation these days, right? So everyone is trying to have all these different tools just to really target very important, large, significant scientific problems, meeting global challenges and so on. So one should not sort of just say, I am a chemist and I will always be just learning chemistry. So we have to learn many different things, peripheral, and learn the jargons to talk to people, to have all these interdisciplinary collaboration. So Ben, you mentioned about very fundamental importance about catalysis, right? And photosynthesis, which is also related to that, it's really the bread and butter and fundamental of the origin of life, right? So how would you see chemistry can contribute even more, or which are the areas you think are so important that we'll be able to make more significant contributions in meeting global challenges?
I think the origin of life is a great topic that you raise. In my society, in the Max Planck Society, right now, this area, the origin of life, is dominated by physicists, astrophysicists, and biologists, which is kind of weird, right? Because as you point out, this is fundamentally a chemistry, by definition, a chemistry question, right? Before it became biology. So I think that's a great area to work on. But for me, actually, right now, what I'm deeply fascinated with, and I mentioned this in my talk, is the CO2 conversion. Picking out, taking the CO2 back from the atmosphere and converting it into something that you can store and you can make energy and all sorts of beautiful things with. I think it's just sort of a grand challenge, and it's so beautiful for us chemists to also contribute to this problem.
So Yi, you talk about, right, earth abundant elements. That's very important as well, right? So and also beyond lithium battery and of course other things. So can you share with us some of your thinkings about how we could contribute more in solving global challenges?
Absolutely. So I want to share maybe just slightly broader of, in chemistry, you look at the past few hundred years has been foundational to build to the building of modern civilization. But looking at the grand challenges right now, climate change, sustainability as an issue, chemistry will be able to contribute to nearly all of the important areas. So let's list that. storing energy I just talked about today, enabling complete sustainable mobility and stationary storage, decarbonize the whole electricity grid, right? That's a very important one. And also looking at decarbonizing, let's say remove CO2 from the air, maybe ban your idea CO2 decomposition, carbon and oxygen. Fantastic. How do you capture CO2 and utilize that? And also natural gas, the methane leakage, right? It's 1.7 ppm concentration. How do we deal with that? This need to rely on chemistry. And then how do you generate clean steel? New type of cement, maybe it's a new chemistry to enable that, right? Low carbon cement, low carbon steel. And then how do you enable hydrogen economy? And how do you do material circularity and new type of agriculture as well, sustainable food generation, instead of utilizing this very CO2 greenhouse gas intense process? This chemistry certainly coupled with biology for sustainable food and agriculture as well. So nearly everything we look into, you got to involve chemistry.
Yeah, thank you. So Peng?
So I guess grand challenges in chemistry, there are many of them, right? And energy technology making batteries. Now, from my point of view is that I have been studying sort of chemical processes. And actually one of the grand challenge processes that I want to study is batteries. And these are solid state reactions. Can
we can collaborate now.
Perhaps. I don't have a good idea yet. How can visualize battery reactions?
We will have lunch together. We'll talk about
okay.
collaboration.
We can talk about that. Okay, talk about that. Now, that Vivian mentioned, as chemists, actually, when we think about chemical process, we always think about individual molecules, right? When we think about organic synthesis, we think about A reacting with B to C. That's what we think. But we never measure that way. Okay, we typically measure a million A's reacting a million with B's, generate a million C's, right? Of course, modern techniques now can allow you to look at individual reactions, but not all of them. Experiments that I talk about are essentially selected examples that I could do it. There are many examples I wanted to do, for example, battery reactions. I don't know how to do that yet. And active materials, can we visualize these things even down to a more molecular level? That'll be fantastic.
I'm doing it.
All right, great.
Okay, so Jinyo?
Oh yes. So actually, from my point of view, the global challenges, there could be many, but at this moment, one very hot topic besides the energies and the preclude energies, there are actually people are starting to work on the complex systems, where the system is out of equilibrium from the AIs, from the air systems, from whatever the live societies. And a lot of these is actually an unexplored area, and for computing as well. There are many things, but from scientific point of views, we as a scientist or whole society, human beings, is trying to work with a thermodynamic system for like hundreds of years. But for the non-equilibrium systems, maybe it's just started. And there are applications there, as I said, there could be AI computings, and it could be possible to build artificial life. And this artificial life is arguably a computing machine. And maybe that is more or less a different ways of thinking what new materials and new application could be. And it could be a little bit far away, but I think it's looking further in the futures that could be.
Yeah, so you also mentioned about some of your micro swimmers, active, colloids and all that. And then they can sort of phase segregate to have the frog skin sort of camouflage and all that. But then you also mentioned a little bit about going to cancer cells or, nanorobots. So because we have been talking quite a lot on energy and catalysis sustainability, what about chemistry in terms of contributing to health? Biology, of course, photosynthesis is one. Yeah. So can you enlighten us on that?
I mean, this is something I try to also mention in my talk. What people who are not chemists forget is that that chemistry actually contributes to our health more than anything else, right? It's not, I mean, nothing against the doctors, they heal us, it's true, but they're not the ones who design and make pharmaceuticals, for example. And one vision I'd like to share with you, I think this is also would be a grand challenge if you start your own career now and you think about what to work on. I would suggest to take a look at bioorthogonal catalysis, right? Bioorthogonal chemistry we know, but can we come up with a catalytic reaction that works orthogonally to the chemistry that is ongoing in our bodies, and then have a catalytic drug? You take a little bit of a pill, like, I don't know, a milligram or something, and that heals some disease that you might have in a catalytic sense. I think that would be something really incredibly useful. So, yeah, just a little suggestion for you guys.
Yeah, very exciting. So just like what you have a PPB level, and then you'll kill yourself. Yeah, okay. So,
well, I think what Ben just said remind my colleagues' work, our Nobel Prize winner, Karen Bartolsi, and that would be really cool. So another area, perhaps, if related to life science, is actually brain. How does brain work? How does the whole body? How do you form recognition and so on? I think this is very rich. It's just not only just biology, it's a lot of chemistry. And there can play a very important role in terms of designing the tools, understanding the molecular level mechanisms, understanding the interconnectivity of different molecular pathways can enable this. This is super exciting. Yeah, I don't work on that anymore. So, but I just for about 10 years I worked with my colleagues, Professor Bin Xiaoqui at Stanford on this. But running out of energy to work on so many things, better concentrate on energy.
But you're amazing. I remember you were trained as an inorganic chemist, and now you're doing all these materials, fantastic materials.
That was why actually Li Yadong was my chemistry professor at USTC in organic chemistry. Yeah.
Okay. Yeah, sure. And Pang?
So maybe one particular area that I should mention is antibiotic resistance. And this is probably one of the biggest issues in health. I don't want to say that I know much, but one of the motivations that we started looking at bacteria of the efflux pumps was sort of motivated by that, because one of the well-known antibiotic resistance mechanism is the efflux. Okay, bacteria is so powerful of pumping every toxic chemical out, and the drugs just do not have effect. And that gave us opportunity to look at proteins, how these proteins inside the cell. I cannot say, I'm not sure whether I will be able to say that we ever provided any solution to antibiotic resistance, but looking at these fundamental chemical processes of how these proteins work together has been a very rewarding experience. And I think maybe for other younger researchers looking into these type of issues will be exciting as well.
Yeah, but it's really interesting. You have this sequence specific. You were able to work out the sequence of all these copolymers and so on. It's really amazing. Yeah. So Jinyo, can you share with us?
Oh yes. So I think it's for health. Obviously, we're working with something very different with other like we ordinarily work on. Like ordinarily we like ourselves. Like life is a complex system again. It's thermodynamically not equilibrium, like far from equilibrium actually. And nowadays, people are working with the drugs or a lot of the case that it could be bindings onto certain targets, but later on they actually failed. So I think this is a shortfall for current research where we think this life can be like just like piece by piece together instead of a holistic view of what life is, and they are far from equilibrium. There could be amplifications. Those kind of works requires different kind of mathematic calculations or method, and also different kind of statistics calculations, or as well as a theories, and maybe like as active matter chemists, actually, like we think we're making insight into their area. Of course, another thing, as you can already see, a lot of the researchers in my area is trying to make the drug delivery things. I think it's a little bit far or a little bit too rush, but it could be the futures.
So thank you very much. So time is up. So thank you very much for all the very insightful advices to our young people. And it has been a wonderful time having you here in the panel. And can we give a round of applause for all our speakers?
Thank you so much for insightful sharing. Could you please rise and then we can have a photo together? Let's have a photo together. And then, okay, our official photographer is ready. Just have a look to the center, please. Maybe we can have the photo first, if you don't mind. Yes, please. Thank you. Okay, please continue to have a look to the center. One, two, three. 1, 2, 3. 1, 2, 3. Okay, one more to go. One more to go. 我们再来一张。1, 2, 3. 1, 2, 3. Okay. Thank you. Thank you so much. Thank you very much for the insightful sharing. Thanks a lot. Wow, I think this is a really special and very interactive sharing that we understand more about the topic. Thank you so much, everyone. This is the finale of this section. We are about to have lunch. For those who have registered for the lunch, you can just follow the instructions from our helpers to the venue. And then don't forget that we will resume the summit again at 1:30. So we are going to have an amazing keynote speech coming up. So see you at 1:30. Thank you. Hello, ladies and gentlemen, and some students. Thank you for joining the Science Symposium. For the afternoon session is about life science section. We'll be focusing on transformative science for human biology and health. Now, I would like to introduce with you Professor Tony Xu Mok as the section's convener. He is Chairman, Department of Clinical Oncology, Li Shifan Medical Foundation Professor of Clinical Oncology, Chinese University of Hong Kong, Honorary Secretary of the Board of Directors and member, Hong Kong Academy of Sciences, member, Program Committee of the Future Science Prize Week 2024. Please give big hands to Professor Mok.
Thank you. Great pleasure of mine to welcome all of you here this afternoon in the life science session. I'm most excited to see not just the professor, but the young student to be here because you are our future. So as you probably know, life science is one of the most important disciplines of applied sciences in the 21st century. Not that we only study the life phenomena and also review the law of life and activity and the essence of life. Indeed, we're surrounded by biosciences right at this moment. However, we're all facing major challenges in the society this day. Different disease, cancer, cardiovascular disease, food shortage, energy crisis, and environmental pollution. And to solve all these problems, we need bioscience and biotechnology. So today, with great pleasure, we have 4 major speakers, keynote speakers from different disciplines and different parts of the world on very interesting topics. And I here announce the beginning of the life science section, the transformative science for the human biology and health. With that, I would like to introduce our first speaker, Professor Anne Ferguson-Smith, CBE, who is also an Arthur Bethel Professor of Genetics, the ex-Vice Chancellor for the Research and International Partnership in the University of Cambridge, and also the Executive Chair of the Biotechnology and Biological Science and Research Council. More importantly, she's also a fellow of the Royal Society and also the Academy of Medical Science. And she's going to talk to us about interesting topic, epigenetics, what is it, and why is it so important? Anne, may I? Thank you.
Hello, everybody. It's a real pleasure to be here at this fantastic symposium. And this morning was wonderful getting to hear about science outside my own discipline. It's a real luxury to sit and learn about catalysis and longer batteries, and it's really, it really exemplifies the value of hanging out with different disciplines and thinking about how what others do can influence how you think, and how what you do can influence what others think. And so it's a real pleasure to be part of this symposium, and thank you for having me here. So I'm going to talk about epigenetics. And the problem really begins really within the nucleus of a cell. So the nucleus of a cell, of a human cell, is about 6 microns in diameter. And one has to squeeze 2 to 3 meters of DNA into that nucleus. And that DNA is not really, therefore, how we think about it as a double-strand helical structure. Of course, it is that. But it has to be packaged and organized in such a way that it fits. And so what you see here is the DNA, which is modified with DNA methylation here. I'll come back to that in a minute. And it's wound around a structure called a nucleosome, which is made of 4 core histones, in fact, 2 copies of each of the 4 core histones. And these histones have tails. These tails can carry chemical modifications, and that influences how this chromatin is wound into the beautiful structure that is the chromosome. And this chromosome, in humans, there are 26 pairs of chromosomes, and they're packaged and bundled into this nucleus. But it's not just about packaging. This process is highly regulated. And it's regulated in much part by epigenetic modifications, these chemical modifications that sit on the DNA and the histone proteins. So epigenetics, what is epigenetics? There's lots of people who spend a lot of time trying to define it. I don't, but because there are others who do it much better than I. And so over the years, it has had a number of definitions. My favorite one is probably the one most recently from Adrian Bird, who defines epigenetics as the structural adaptation of chromosomal regions so as to register, signal, or perpetuate altered activity states. But for me, really, epigenetics is about the modifications, chemical modifications to DNA and chromatin and their influence on genome function. And the modifications that we think about the most are DNA methylation, this mark that sits on the cytosine when it's next to a CG in mammalian genomes. And then, obviously, it's symmetrical, so it would sit on a C opposite a G here. And the other modifications are these post-translational modifications to the core histones that influence how chromosomes are packaged. And they contribute to, epigenetic modifications evolve to do 3 things. Can I ask, I can't see the bottom of that slide. Can you see it, the third bullet point underneath? Good, okay, because I can't see it from here. So epigenetic modifications evolve to really do 3 things. The first is to contribute to the functional architecture of chromosomes. So what does that mean? These chromosomes have constrictions in the middle called centromeres that are really, really important for the pulling apart of chromosomes into daughter cells during cell replication. And epigenetic modifications act in the regions of these centromeres to make sure that there's strong, robust structures that enable proper segregation of chromosomes. The architecture of the chromosomes is important for that process. The second thing is that they contribute to the dynamic regulation and heritable maintenance of gene expression, particularly during development, and I'll talk a little bit about that. And thirdly, and very importantly, something that we don't think about very often, but they actually have evolved to manage the half of our genome that is repetitive, and I'll talk about that also. And I know that Hai Fan Lin will also talk about the management of repetitive elements by epigenetic states too. So, the epigenome, so while we have one genome in all of our cells, each of our cells has pretty much the same DNA content, we have lots of epigenomes. And that's because the epigenome is both dynamic and stable, and importantly is cell type specific. So for example, in neurons, in brain cells, we need to organize our DNA in such a way that the genes that are required for neuronal function are expressed, are accessible to the machinery of the cells that turns genes on and off, and genes that are important for liver function, for example, are not. And so that's illustrated here, where you can, where you can see areas, for example, where a heart gene might be sitting here in a neuron. It's closed, it's modified, it's marked with repressive modifications that ensure that that chromatin is tightly packaged, whereas genes that are required to be expressed are in a more open state. And that is, of course, regulated by transcription. Gene expression is regulated by transcription factors, but those transcription factors are interacting with the epigenetic machinery, which is maintaining this gene in an open state. Similarly, in a cardiomyocyte, a heart cell, we have a heart gene that is marked with modifications that keep it open and adjacent to, for example, brain genes that have to be closed so that the wrong genes don't get expressed in particular cells. Epigenetic marks are generated and acted upon by enzymes and proteins that write the mark, that read the mark, and then can remove the mark in contexts where the epigenetic state is dynamic. And many of these readers and writers and erasers have been well characterized, and some of them have been, the expression of some of them have been perturbed in cancer cells, for example, resulting in abnormal epigenetic modifications, epigenetic states in cancer. And furthermore, some of these readers have been targeted as therapeutic agents for drugs in particular cancers. So there is a growing field in epigenetic therapies, particularly in cancer. But importantly, and I'm going to focus predominantly today on DNA methylation because that's the mark that we work on the most. It is a mark that is stably maintained during cell division, and that's because a methylation at a CG, the enzymatic machinery that places new methylation marks on before there was none, recognizes that newly synthesized strand of DNA with the CpG dinucleotide, recognizes is at a cross from the old strand that is already methylated, so the enzyme recognizes so-called hemimethylated DNA and puts methylation on. So it sees the methylation on the old strand and puts it on the new strand. And that means that there is a mitotic heritability. There is the ability to inherit a methylation state from a parent cell to a daughter cell. Now that is different from heritability from one parent generation to children, to offspring, which is going through a germline. And that is a different process and a different mechanism. And it's very hard to imagine epigenetic inheritance from a parent to offspring because in mammals, the epigenetic marks are erased and reconstructed from one generation to the next. So the epigenetic memory that is established in one parent is generally lost from one generation to the next. And that's illustrated here on the next slide, where you can see, which is a graphical representation of the dynamics of DNA methylation in the two periods where epigenetic marks are erased and reconstructed. The first is during the development of eggs and sperms. These are primordial germ cells, cells that are going to become the eggs and the sperms. And as they develop, this is data from the mouse, by about little after mid-gestation in a mouse embryo, all the epigenetic marks, including DNA methylation, have been erased. The germ cell, the nucleus, the DNA is epigenetically naked. And then in the male germline and in the female germline, in the making of sperm and in the making of eggs, new marks are placed on in order that the genes that are important for making sperm and the genes important for an oocyte function are properly regulated. And then upon fertilization, lo and behold, the whole thing happens again, and the male germline loses loses its epigenetic marks actually quite quickly, and the female germline loses her epigenetic marks. The female chromosomes lose their epigenetic marks a little bit more slowly. And then around the time the embryo implants in the mother's uterus, they start to get those marks back again, and those marks occur in a tissue-specific and cell type-specific manner in the way in which I explained to you in the very first slide. So if we have this erasure and reconstruction not once but twice in mammalian development, it begs the question about epigenetic inheritance, and that's what I'm going to talk about for the last part of the last half of my talk. So really, the idea here is that the question really is, to what extent are methylation states that are established in one generation transmitted to the next? Can they be? If I've told you that they're generally erased and reconstructed, a lot of interest in epigenetic inheritance. How can that happen if these marks are erased and reconstructed? And then the next question, which is a pervasive question in the field, is that does the environment talk to the genome via the epigenome? And if it does, can that change, can that influence be perpetuated across generations? Remember, the template for our inheritance is our DNA, is our genetic material, but is there a role for epigenetics? And so to answer, I'm not going to answer those questions completely, but I'm going to be provocative and explore them with you for the rest of my talk. So I'm going to talk about my two favorite models of so-called epigenetic inheritance. One is a process called genomic imprinting, which I've worked on for many years, which is a true model of epigenetic inheritance, and we understand how that works. And then the second model I'm going to talk to you about is associated with these repetitive sequences, these regions of the genome that actually look like viruses and have the potential to mobilize and hence are targeted by the epigenetic machinery. Let's explore a little bit about their epigenetic inheritance. And this is to remind, this sentence at the bottom about the value of inbred laboratory mice is to remind me to tell you that I'm a fundamental, basic researcher. I'm not working on translation. My interests are in making conceptual advances in our understanding of molecular genetics, and that particularly for epigenetic studies, the laboratory mouse is a really good model for looking at this, because you can breed laboratory mice such that they are genetically homogeneous. If you were to do this kind of things in people, all of you in the room have different genotypes from each other, and many of the epigenetic changes that one finds in you will be because they're sitting on top of perhaps a sequence polymorphism where the CPG that should be that is methylated in some of you has been changed to a TG and therefore isn't methylated, and that's a genetic rather than an epigenetic change. It's a genetic change that underpins an epigenetic change. And by using inbred strains of mice that are genetically homogeneous, we get away from that genetic variation and makes this a very good model for studying both epigenetic variation and epigenetic inheritance. So I'm going to start to talk with genomic imprinting. And to do that, I want to go back to basics, because I know that there are physicists in the room, and to remind you that upon fertilization, the embryo inherits one set of chromosomes from the egg and one set of chromosomes from the sperm. And I've illustrated these here as, you know, as a blue set from dad and a red set from mum. So 2 copies of every chromosome, apart from the sex chromosomes. That's not relevant at the moment if you're a male. I'm talking here about non-sex chromosomes. So what is genomic imprinting? Well, when I was a graduate student, I read the most amazing piece of work, and it was published in 1984, which is, and so this year, this discovery is celebrating its 40th anniversary. And it was this experiment here done independently by 2 researchers, 2 embryologists, one called Azim Sarani in Cambridge, and the other called Davor Salter, which doing work that he did when he was in Germany. And what they discovered, oh no, maybe he was in the US when he did the original experiment. So what they did was they took a newly fertilized mouse egg and they removed the male pronucleus. This is the bag of chromosomes that came in from the sperm. They whipped them out and replaced them with a second set of chromosomes that came from mum. Alternatively, they whipped out the bag of chromosomes that had just come in, that are just coming in from the egg, and replaced them with a second set of chromosomes that had come from dad. So they generated embryos that had the normal chromosome complements in terms of numbers. So they were a normal diploid set of cells, but they had altered the parental origin of the chromosomes. So, so what they discovered, and here's the nice control in the middle, which has the normal set of chromosomes from dad, set of chromosomes from mum. And what they discovered was that these two experimental embryo types could not make it to term. They failed, despite having the normal genetic chromosomal constitution. What happened here is if you have two copies from dad and none from mum, you make a lot of extra embryonic tissue, and very rarely do you get an embryo at all. This is the embryo, and it's very retarded and very underdeveloped, and it's, but as I say often, it's just not there at all. And on the diploid maternal or gynogenetic conceptus, you get a rather nice-looking embryo proper. You get very pathetic extra embryonic tissues, but the embryo itself is very small. And these embryos, as I say, will die. And so what this said, what this told us was that actually being diploid is not enough. You need both a maternal and a paternal set of chromosomes in order to develop as a mammalian embryo. It also told us that the maternally inherited chromosomes function differently to the paternally inherited ones. Now, this is what blew my mind when I was a graduate student, because Mendelian genetics told us that, you know, you've got these genes from mum, these genes from dad, and you have two copies, and they're both either expressed or repressed at the same time. This was telling us that these chromosomes were functioning differently. It also suggested that there was something about the maternally inherited chromosomes that looked different from the paternally inherited ones, even though they were genetically pretty much the same. And then finally, it suggested that there was a memory, some kind of memory of parental origin that was conferring these functional differences on these two chromosome homologs in the newly fertilized, in the embryo during embryogenesis. This is not a mouse thing. This happens in humans as well. An androgenetic conceptus in humans is a complete hydatidiform mole, which is a diploid bipaternal contribution. It resembles a malignant mass, and like the mouse, it has an excessive cytotrophoblast proliferation. The extraembryonic cells are overproliferative. And the diploid maternal is known as an ovarian teratoma, which is a germ cell tumor of the egg. So it's a sort of activation of the female chromosomes. It's usually benign, and it contains tissue lineages such as bone and hair and teeth. So it has embryonic components to it rather than extra embryonic components to maternal genomes. So we now know that this process of so-called genomic imprinting is a process that causes genes to be expressed differently depending on whether they've come from the mother or from the father. So these two chromosomes, they look the same genetically. They both contain gene A, and although the sequence of gene A is to all intents and purposes the same, apart from polymorphisms between males and females, only this one that's been inherited from mum is expressed, the other one is repressed. Likewise, another gene nearby even is expressed from the paternally inherited chromosome and not from the maternally inherited one. Whereas most other genes are either expressed from both or repressed from both. They behave in the same way. So over the course of many years, we and others have tried to understand this mechanism, to try and understand what it is that's different about these two parental chromosomes. We know that this is due to differential epigenetic modifications. So the DNA may be the same, but the epigenetic marks are different on the two parental chromosomes. So what do these genes do, these special imprinted genes? Well, they're very important for development. They're very important in prenatal growth and placentation. They play a particular role in the development of particular lineages, such as bone and cartilage. This is a developing placenta. We know that they play a role in postnatal and prenatal, in fact, brain and behavior. Imprinted genes are important in the regulation of adult neurogenesis, for example. And we know that they're important for postnatal life course events. So this is a model whereby the mice the mice don't do non-shivering thermogenesis properly. They cannot control their temperature properly, and that's because of the altered dosage of imprinted genes. So they play a role in fat metabolism and other postnatal physiological processes. In humans, you can have alterations in these imprinted genes, and they result in imprinted syndromes. Imprinted genes generally hang out in clusters. There's multiple imprinted genes alongside each other, and these clusters get perturbed, or you get when they get perturbed, or you get loss of imprinting, you end up with imprinted syndromes. And there are 8 human imprinted disorders that have been characterized to date, and they are generally associated with 3 types of mechanisms. Either an alteration in the dosage of the parental chromosomes. So you can see here that if you have 2 paternal chromosomes instead of one from mum and one from dad, you get a double dose of gene A, and that's bad for you. You can also have a deletion, and if the deletion happens in the active copy of gene A, then you're basically not making any of gene A, or you're functionally haploid through imprinting. Alternatively, if you were to lose this copy, nothing would happen because it's the paternal one that's being expressed. An example of an imprinted gene actually is the insulin-like growth factor 2 gene, which is very, very important for development when you're an embryo. And it's only expressed from the copy that you inherited from your dad. The copy that you got from your mum is silent. And so if something like this happened, and you ended up with 2 copies of your dad's chromosome and none from your mum, you'd be making a double dose of this insulin-like growth factor 2 gene. You'd be really big, and you'd also have an increased incidence of childhood cancers. So that's the sort of relevance of imprinting in human contexts. So how does the transcriptional machinery, how does the gene expression machinery tell the difference between these 2 parental chromosomes and express one and not another? Well, it's because the genomic imprinting is actually a DNA methylation mark that is placed differently on the imprinted chromosomes in the egg compared to in the sperm. So, and there's about 20 imprints that are established in the egg. This is DNA, a filled lollipop means methylated DNA. In the vicinity of this gene. And likewise in the sperm, there are actually only 3 imprinting control regions in the sperm. They're never at the promoters of genes. They're usually in the middle of the, in between genes. And upon fertilization, you end up inheriting an unmethylated copy from dad and a methylated copy from mum. And DNA methylation is generally associated with repression. And so this copy is active and this copy is repressed. And likewise, you inherit a methylated copy from the dad, an unmethylated copy from the mum. You're differentially methylated between the 2 parental chromosomes. So imprints are regulated by germline-derived differentially methylated regions, which are heritably maintained in offspring after fertilization, and often a single differentially methylated region. An imprinting is an imprinting control region for lots of genes in the cluster. So how can that happen when I told you that, that these epigenetic marks are erased and reconstructed? How can you remember, how can you have a memory, an epigenetic memory of these parental imprints in a context where upon fertilization everything is lost? Well, what we know is that it's not the germline methylation that is the essential component of epigenetic inheritance at imprints, because actually there's lots of regions of the genome that are differentially methylated between eggs and sperms, but it's the retention of that methylation after fertilization that is absolutely the key. And that is regulated by, so that is illustrated here, where you see a context where all the rest of the genome is losing its marks, but imprinted germline DMRs are retaining theirs. And they're retaining them through the presence of 2 proteins called crab-zinc finger proteins that bind to these methylated regions and target a continuous acquisition of methylation, so the memory is retained. And we know that because when we mutate these 2 proteins in the mouse, the imprinting memory is lost. The animals lose their memory of parental origin. I want to say a little bit about these proteins because we don't know people don't really know very much about them, and they're really interesting. They're a family of DNA binding proteins that are unique to vertebrates, and there's hundreds of them. They recruit the repressive chromatin complexes, resulting in the writing of repressive histone modifications and DNA methylation. And they're very different between different species. Of the 300 or so, only 80 of them are common to mouse and human, and that's actually quite unusual for important regulators. For imprints, these are they're 2-methylation-sensitive crab zinc finger proteins. They bind to methylated DNA, but most of them don't. Most of them are actually targeting methylation to regions that are previously unmethylated. And what they really evolved to do was to target the 50% of our genomes that are highly repetitive, look like viral sequences, and have the ability to move around. And so that brings me to the second part of my talk. For the last 5 minutes or so, I'll tell you about variable DNA methylation at transposons. I'm going to have to whiz through this. So this is to just tell you that retrotransposons are substantial. So this is a whole bunch of different organisms. They all have some kind of repetitive sequences within them, but the mouse and human have close to 40 to 50% of their genomes are made up of these repetitive sequences. And they're targeted after fertilization by the repressive chromatin machinery and DNA methylation via these crab zinc finger proteins. And I think you'll hear from Haifan how these particular sequences are treated in the male and female germlines, in the germlines in particular. I don't know if he's going to talk about that or not, but he might. But many of these elements have lost the ability to mobilize, so they're actually just sitting there. They're broken, but yet they're still targeted by the epigenetic machinery. So the second model that I'm excited about in this context is a classic mouse model called agouti viable yellow. So these 6 mice look very, very different, but they're actually genetically identical. So their coat colors are ranging from yellow to brown and everything in between, yet they're genetically identical. So what's happened here? Well, one of these repetitive sequences, called an IAP, has inserted upstream of the coat color gene and provided a regulatory sequence that inappropriately turns this gene on. And when you turn this coat color gene on too much, you get a yellow mouse. And when you don't turn it on at all, you get a brown mouse. And the ability to turn the gene on depends on whether this retrotransposon has been methylated or not. So these yellow mice have no methylation on their transposon, yet the brown ones, called pseudoagouti, have very high methylation. And the mottled mice have levels of methylation in between. So here we have a visible phenotype that is regulated not by genetics, but by epigenetics. And this mouse model is a very exciting one because it's quite sensitive to environmental factors. So you can feed mice methyl donors, and you increase the methylation at these, and you shift the coat color. You can also treat pregnant females with the endocrine disruptor bisphenol A, and you shift the coat color towards yellow. So it's a model of environmental compromise. In addition, and most importantly, it displays transgenerational epigenetic inheritance, apparently. And what you see here is that yellow mice are much more likely to have yellow offspring, and brown mice are much more likely to have brown offspring. And I told you that the color is conferred by the epigenetics, not the genetics. Therefore, that propensity is epigenetically inherited. So how does that happen? When I told you that the epigenome is erased and reconstructed, what happens at agouti viable yellow? Well, we know that the methylation is actually treated the same way as the rest of the genome, not like imprints. So in this case, the epigenetic memory is erased and reconstructed. And we actually, in contrast to imprints, we don't know the mechanism of epigenetic inheritance at this mutant. We wanted to ask whether this particular agouti viable yellow was special, or whether any of the other 10,000 transposons of this particular class behaved in this way too in the genome. So we did a genome-wide screen for repetitive elements that behaved like the one at agouti viable yellow, and we found about 100 of them. Some of them are influencing genes, some of them are not. They're very young, they've recently jumped into the mouse genome. We know that the mechanism is conferred by these crab zinc finger proteins who don't do it very well, and as a result, you get inter-individual variation in methylation. And we wanted to ask whether it was these elements were environmentally sensitive and what their patterns of inheritance was. And I'm conscious of time, so I'll be very quick to say, basically, to cut a long story short, they're not environmentally sensitive. They don't respond to the environment. So agouti viable yellow seems to be special in that context. And that's just the methyl donor diet, so showing no effect. And that heritability is the exception rather than the rule. So in fact, most of them don't show any epigenetic inheritance. So what I've told you really, I hope, is that epigenetic modifications are important. They sit upon our genetic material and they influence how genes are expressed or not. But importantly, in mammals, they are erased and reconstructed between generations, which means that it's difficult to inherit an epigenome from one generation to the next, except at very special places where it's very highly regulated, such as genomic imprints. Epigenetic modifications evolved to silence these repetitive sequences in our genome, to target these sequences, and they do it usually very well. But some are not fully silenced and can influence adjacent gene expression, like I showed you for agouti viable yellow. So these are epigenetic effects. Agouti viable yellow is an epigenetic effect that causes differences between individuals. Not genetic effects, but epigenetic effects. And that, I think, has non-genetic implications for disease, and actually even for normal outcomes that might explain why some of us are different from each other, not for genetic reasons, but because our repetitive sequences have variable epigenetic states that influence the expression of adjacent genes that cause differences between us. And we have evidence now in mouse that I didn't have a chance to talk to you to say that in fact this is true, and it's quite important, for example, for metabolic phenotypes and other phenotypes that are relevant for complex disease. So I'll stop there and thank the people in my team who've done the work. The work that I talked about is predominantly being done by this team here, predominantly Kevin Costello and Nozomi Takahashi. And I thank our funders and our collaborators who worked on the environmental modulation stuff with us, and I thank you for your attention.
Thank you, Anne, for the marvelous talk on epigenetic. Now I know who I am, why I am is actually related to my epigenetic. Hopefully one day they can modify my epigenome a bit better to make me a bit smarter. So with further ado, I would like to introduce the next speaker, who is Professor Ewan Ashley, the Associate Dean of the School of Medicine, also the Roger and Joelle Burnell Professor of Genomics and Precision Health. He's also the Professor of Medicine in Cardiovascular Medicine, of Genetic, and also of the Biomedical Data Science, and also by courtesy of Pathology. So he's a professor of many things. More importantly, I read his CV, and one of his lifelong interests is looking at the health impact of the Scotch single malt whiskey, which I would very much like to participate in his experiment. So he is going to talk to us about realizing the potential of biomedical AI. Ewan, thank you.
I am very grateful to Anne for tuning your ears to a Scottish accent just in time for the second Scottish speaker of the day. Thank you for the invitation from the committee to join you today to talk about artificial intelligence. We are in the middle of a revolution in machine intelligence that will touch very many aspects of our lives, and I'm going to focus today, of course, on how that will affect us in science and how that will affect us in medicine. Here are my financial disclosures. Many of the images, including the one you saw on the last slide, are generated by AI. I think, surprisingly, this image is not generated by AI and comes from the James Webb Telescope. This is the Carina Nebula, 7,000 light years away. But I think the quote from Arthur C. Clarke is pretty relevant to the way many of us are thinking about artificial intelligence today. Some of the things it can do are indistinguishable from magic. And AI has surpassed humans at a very large number of tasks. And more importantly, the rate at which humans are being surpassed is increasing. If you look at this graph from the late 1990s to now, the slope of these lines as AI beat us at handwriting recognition. For doctors, that's not surprising, maybe. Language understanding, reading comprehension, image recognition. Even since this graph was made in 2022, AI has surpassed not just grade school math, but high school math and now college math. So the rate at which it is improving is remarkable and is increasing. Since 2023, these multimodal AIs can understand and explain complex images and diagrams. It can break down an image like this and explain it to you in multiple steps. It can even make me multilingual. I don't know if the audio will. You can't hear the audio. Okay, you just have to believe me that this is me speaking in Japanese. That doesn't really work with the audio, unfortunately. Well, anyway, I have Mandarin in there as well, as Polish and Spanish. And the most freaky one, actually, of all, is me speaking with an English accent, which is quite strange. Anyway, I'm very sorry that you've missed that. I guess the audio later will not work either, but never mind. AI can also remarkably talk to animals, including whales, and even plants. This is a paper in Cell from just last year, looking at the sounds emitted by plants under stress and essentially parsing them using artificial intelligence. Also, perhaps most remarkably, there are emerging properties of these artificial intelligence models where they appear to even have a theory of mind. So if you look at this little diagram shown here, just for a moment, I'll let you take it in with your human brain. Well, I think you see a cartoon where there are three adults and they think they agree, but they do not. They start talking and then they realize they don't agree and then they come to a compromise and at the end they all agree. The fact that we can understand that relates to the fact we are human and we understand what it is to interact with other humans. How does a large language model interpret this from the perspective of a human cognition? I say appears to have a theory of mind. These language models do not have a theory of mind, but they do a pretty good job of appearing to understand what it would be like to be inside a human brain. And I think it would have hardly escaped your notice that in the last couple of weeks, AI has swept the 2024 Nobel Prizes, both in physics, some debate about whether it really was physics, but certainly physics with Jeff Hinton, John Hopfield, and the chemistry Nobel for AlphaFold, Demis Hassabis, and John Jumper, and obviously David Baker there as well. Related to health and medicine, it's and somewhat more challenging for those of us who are practicing doctors. It turns out AI may be more empathetic than doctors. In this study of 195 randomly drawn patient questions from social media, both doctors and an AI responded, and then they were judged by both patients and doctors as to which were the more empathetic. And both the patients and the doctors judged the answers from the AI to be more empathetic than the answers from the doctors. So we may be out of a job yet, although I'll come to some reasons why it may not be just today. Before we go forward, I want to go back. How did we get here? And the history of AI is actually probably quite a lot longer than most of you would remember, or perhaps even appreciate. The term artificial intelligence was first coined by John McCarthy and some other authors from MIT and Stanford in the 1950s. But even in 1950, you could trace back to when Alan Turing first published his classic paper outlining the Turing test in Cambridge. From then, through the 60s and early 70s, there were many breakthroughs, most of which were bi-coastal in the US between Stanford and MIT, actually shown in the back of this diagram. The reason you can see the Stanford campus through the middle of this history is because there was an AI winter for about 30 years. Very little happened, even arguably 40 years up to the early part of 2010, when suddenly we were in the deep learning era. And I'll pick up that history with the next couple of slides. You might remember the first time that an artificial intelligence algorithm was applied to the entirety of YouTube. It found two themes. One of them was human faces, and the other one was cats. Maybe not surprising to many of you who spend time on YouTube. But that entered us into the deep learning era, the era when you could ask a model what was contained within a photo, and it would use a series of deep learning algorithms to identify them, as shown here on the right. This was work pioneered by many, but including Jeff Hinton, one of those who just won the Nobel Prize and previously had won the Turing Award. And it really involved, for the first time, the bringing together of several different elements, including the training on very large data sets, the use of GPUs for that training, very deep models, through which backpropagation allowed optimization of those models in a way that may or arguably may not be similar to our human brain. This was around 2010, 2012. You may have seen this image before. Of course, it's a little bit of a test for a vision model and even for a human to tell the difference. Of course, in those days, it was a little different for those models to do that, a little difficult. These days, you just ask ChatGPT or similar, and it will actually lay out in a table for you which is a chihuahua and which is a muffin, which is helpful, obviously, in the real world. Maybe not. One of the most really important elements beyond deep learning, beyond the convolutional neural network that underlay those previous slides, was reinforcement learning, and this does not have audio, so you're missing nothing here. This is a classic paper from DeepMind, where they fed in basically Atari games, so some of the earliest games from the 1980s, I think, in computing, and basically fed it individual stills with different training episodes, and basically told it to maximize the score. And it basically came up then in the video domain, sort of in a temporal domain, with an approach to playing the game. As you'll see, it gets better after 400 episodes. Training episodes, until at which point it learned something that humans eventually also learned about this game, and some of you in the audience may be old enough to remember this game, some of you may not. But after, I think it's 600 training episodes, you'll see, yeah, here we go. The agent actually finds and exploits a new strategy. I used to play this game, and it took a little while, but watch. It basically learns that if you fire the ball up in the back, it'll actually bounce up and down and give you many more scores. So reinforcement learning, although it was here learning a computer game, and an older computer game at that, they actually were able to train the same model to play all the Atari games that had been released over the course of a decade and more, and become better than humans almost instantly. This was just the beginning of the world we're currently in, where we have seen computers essentially in these models exceed human intelligence in a number of different ways. Of course, there was the AlphaGo, also from DeepMind, applying the same reinforcement learning, not just to chess as it had done, where it caught up on IBM's earlier win over Garry Kasparov, but this much more complex game that where rules couldn't be programmed in just because of the almost infinite nature of possibilities on a Go board. But learning by reinforcement learning allowed it to play itself millions of times. And you may remember this kind of rather famous victory over, by a mile, the world's best player at the time, Lee Sedol. And then we come up to the current era, and things have begun to move even faster in the last couple of years. You may remember the moment that ChatGPT was released to the world, and they, I think, almost over the course of a month, had 200 million users, the fastest growing user base of any app in all time, including of Facebook and other of those early models. And that takes us kind of up to date for where we are in our run through the history of AI. So the focus here is, where's the potential for medical AI? So I'll talk a little bit about analyzing images and videos. I'll show you some examples of reducing the burden of paperwork in our healthcare systems, very important, helping make difficult diagnoses. I won't talk much about scaling humanity, but I think this is one of the most interesting areas for the application of AI. Not everyone has access to empathy. Not everyone has access to a doctor with specialist expertise. These AIs can help, I truly believe. Also, we know that education is better if there's one-to-one interactions. We know that behavioral change is better with one-to-one interactions. But again, there aren't enough cognitive therapists, there aren't enough training coaches, there aren't enough educators to allow everyone to get one-to-one education or training. AI can likely help there too. And finally, drug development. I'll talk just a little bit about some of the scientific leaning approaches to these models. All right, so this is some work from our group from just a few years ago. At this point, these convolutional neural network models had been applied to chest x-rays, had been applied to CT scans of the chest and the abdomen and various other places. But at that point, no one had actually built a video model. And being a cardiologist and being focused on the only organ that is in constant motion, about 3 billion times during your life, we thought we should build a model for that. And looking at the ejection fraction, which is the amount of blood ejected per beat from the left ventricle, shown here in blue, that is something that is done manually still across the world by millions of individuals on a daily basis. We were able to train an AI to do that better than a human reader and more instantly, and particularly in the form of arrhythmia shown on the far right, it could do it across many more heartbeats than a human could. And I refer you to the paper for more details. Humans will typically take in many modes of data when they see a new patient. So we would see an electrocardiogram, for example. We'd see an echocardiogram. We might have MRIs, and I'll come back to models that can incorporate all of that data. From this work, just again, a handful of years ago, we fed in both ECGs and echocardiograms and asked the model to tell us whether the patient had a Mendelian disease called hypertrophic cardiomyopathy or had a thick heart because they had high blood pressure. And we have obviously had a training data set that we fed in. And then the details are shown here for our LVH fusion model. Pretty good at predicting hypertension, a little less good at predicting hypertrophic cardiomyopathy. In head-to-head comparison, though, our model was already better than its human counterparts, including some humans who had spent 20 years of their career trying to diagnose hypertrophic cardiomyopathy. I was one of those who was beaten by the AI, so humbling us all. We can also ask the AI, like, what are you looking at? What are you using in this video or in this image to help make your decision? And what it found is that it recapitulated 100 years of learning. Here's T-wave inversion in this electrocardiogram at the top, the asymmetric septal hypertrophy of the left ventricle shown in the echocardiogram at the bottom. Large language models, of course, like the kind that ChatGPT and Google's Gemini and Claude and others are based on, it really came from a series of technical advancements that relate to something called attention. I don't have time, I think, today to really go through that in detail, but attention and multiple heads within a network that kind of refers to itself were some of the individual elements of the kernels that are inside large language models that allowed us to move into this current era. And so when you teach these models medicine, or in some cases you don't even have to, you just need to give them enough data, they start to perform better than humans on medical exams. So this was the first paper demonstrating this. At this point, if you look in the graph here, you'll see that over the course of the move from MedPAM to MedPAM2, this particular model went from being at the level of an average medical student to the point of being an expert medical student. So they did the same in the law degree courses and education courses and many others. These are the medical exams. But these models are surpassing us all around. And this might be illustrated better by this example, for those of you who are a little medical in the class, or those of you who are not. I give you this example from GPT 3.5. I just got, thinking of myself, I just got out of a 12 hours of air travel, and my left calf hurts. I also have a little trouble breathing, and I wonder what that could be. So we fed this question into GPT 3.5, and it said, do you have any pre-existing medical conditions? I said, no. It said, in that case, I recommend starting with some light stretches, such as the ones below for your left calf and diaphragm. I hope all of you would have a sense that that might not be the answer, and maybe we should take a little bit more care. Fortunately, GPT-4 takes a little bit more care. Says, I'm really sorry to hear you're experiencing these symptoms. It's important to take this seriously. This could be a pulmonary embolism. Indeed, that's exactly what it could be. Those are the cardinal symptoms of a pulmonary embolism, and you should seek medical attention immediately. So this is a change from GPT 3.5 to 4, partly reflecting the fact that these models are just doing better. This idea of the factuality of the answer, because remember, these models simply are next token generators. They basically have a probability of the most likely word from their huge training data, and they put that word together. They don't have knowledge, despite the appearance of even a theory of mind that I showed earlier. This is a paper that we contributed to that's published in one of the new journals, New England Journal of Medicine AI, using a very kind of hot topic in AI at the moment, which is called RAG, basically Retrieval Augmented Generative Data. So a combination model that uses both next token prediction to just come up with words, but also references specific facts to bring you back facts And if you look in the table at the bottom, you'll see that compared to ChatGPT-4 or Bing or Bard, there's the Google version, Almanac, which is our model trained on medical data, was much more factual in its responses as a result of not just doing next token prediction. Also from the same journal, actually, these two papers are the two most cited papers since the start of this journal, but it's pretty early days, it's only been going for a couple of years, was this paper from the Google team that purported to be able to bring in MRIs and ECGs and X-rays and really multimodal data and essentially interpret it from the perspective of medical diagnosis and treatment. And they even turned it into a conversational agent, so an agent that you could essentially have a conversation with the patient. Tested that against primary care doctors and found, as judged by subspecialists, that it was more accurate and more empathetic, something that I mentioned earlier. So one of the questions I promised to answer at the beginning, are we using this in current clinical practice? This is our adult hospital at Stanford, where the patients from these different rooms get a view of the hills. We are using the GPT version that's embedded in our medical record to start to help answer questions that patients send us. So there's a generated reply shown here, for example, as a potential email that you can use to respond to a patient, and then you get to edit it and send it off. Here's another one where the model actually suggests some specific medical therapy that might be possible for the doctor, and again, you get to edit it before sending it back. So this is a use case. This one was actually studied to see if it reduced the amount of time that was spent. In actual fact, interestingly, it did not. If you look at the underlined area, it improved the mental task load and work exhaustion felt by doctors, very important in an era of burnout, but it actually did not save time. So this is a pilot rollout at Stanford in collaboration with both ChatGPT and Microsoft. Another of those is ambient scribes. So you may have been to the doctor and they may have spent a lot of time typing on a keyboard your notes at the same time, and it's clicking, clacking away in the background. Wouldn't it be better if an AI could just listen to your conversation and write the note for you? Well, it turns out it can. So we have a system called DAX Copilot, again from Microsoft, Nuance, and Epic, that these came from my nurse who sent these to me last night, so hot off the press. You basically turn on your phone, you start the AI system, and it listens to the conversation you have with the patient, and then literally populates your note, shown here in the Epic system. And here's some of the notes that she did yesterday. So it's actually here today, and something that we're absolutely using to try and reduce the burden of paperwork for doctors. In this paper, if you're interested, we discussed quite a lot more about how AI is being used in molecular medicine, specific examples from genomics and immunomics and other elements that are being used in the lab from a pathology perspective. We used a deep variant, which is a variant caller from Google for our whole genome work, and it is easily, for long-read sequencing, the best variant caller that is currently on the market, and it's based on a convolutional neural network. So it basically makes the pile-up, if you're familiar with how genomic sequencing works with next generation. You essentially pile up the individual words that are read by the sequencer against the reference, and you basically look at that pile-up and read down each vertical. In this case, they turn that picture into literally a picture and have the artificial intelligence organ essentially read out the variant. The top-level evidence always comes from randomized controlled trials. So you may be asking, are there any for AIs in clinical care? There's only one that I'm aware of that actually has clear mortality benefit outcome. So this is from China, so a little closer to here than where I normally stand. And this is an important paper published in Nature Medicine, as I say, to my knowledge, the only so far randomized controlled trial showing a mortality benefit. This is an AI that looks at the ECG of every patient who came in during the trial and basically sent an alert as low risk or high risk to the doctors. That was it. Didn't do anything more sophisticated than that. But that intervention alone allowed the doctors to spend more time focused on the patients that really need it. And we believe, the authors would proclaim, and I think I believe them, that alone was enough to change the outcome at 30, 60, and 90 days as shown in the graph at the bottom right. So pretty stunning effect, would need to be replicated in other places, but certainly pretty interesting approach to the application of AI in clinical care. And then I wanted to give you something pretty up to date. We released this paper just 10 days ago, and this is a continuation of our work with the Google team, the conversational agent I mentioned a few moments ago. And in this case, we basically take in the reports from ECGs and echoes and MRIs and the genomics for a patient with Mendelian heart disease and basically have conversations with either general cardiologists or subspecialist cardiologists and eventually also with the patients. But we here have the subspecialists judge the workup of the general cardiologist for these patients and then compare that with the conversational agent from Google. And in this case, we showed that even off the bat, the conversational agent from Google actually outperformed the general cardiologist. When we let them work together, as in discuss the case together, they performed significantly better. You can see in red here, shown at the top. The cardiologist, together with Amy, the conversational agent, massively outperformed the general cardiologist without the agent. And this is just to give you an idea of what that might look like. Here, this is a GP talking to the conversational agent. I have this 69-year-old with some interesting findings. The AI says, happy to help. It's always in a good mood. It's always happy to help. I've reviewed the data. What concerns you? And so the GP can ask specific questions. Well, this echo shows this and that, and I'm a little concerned about that. And the AI responds, and so the conversation continues, and they go back and forth. And this is essentially like a specialist cardiologist available to the general cardiologist or to a GP who would then, at the end, get to the point of having a better ability to judge what was required next. So this is the sort of thing that we're currently rolling out and testing actually in our clinics. When we released this paper about 10 days ago, just talking of other general AI things, and you're not going to be able to hear this since it's an audio clip, so maybe I'll say nothing more about it. But there's actually a tool now that will generate a podcast from your paper. So many of you might listen to podcasts. Usually it's two people talking about something together. We fed the PDF of our paper into this tool, and it basically created a very real-sounding podcast between two people who then discussed the paper. And if you're interested in that, if you look either on social media or there's a link on the paper on archive, you can link through to the generative audio of the podcast, and it is quite remarkable. This has just in the last few weeks become kind of a viral tool, Notebook LMM. You can see the date, September.
Hey everyone, welcome to another
here it is.
dive.
The audio did work.
Because today we are going deep into the world of AI.
In medicine.
In medicine, yeah. And how it could change how we think about specialist care.
Yeah.
You know, like how we access it, how effective it is.
This is entirely generated
robot doctors?
by an AI.
Like, is that what
these
we're
people do
talking
not
about
exist?
Because that is what I'm imagining. You know, like in those movies where it's like all these like, you know, blinking lights and stuff. Anyway.
Well, not quite. It's more nuanced than that, but also really exciting.
So you can hear how they talk to each other. You can hear the breathing. You can hear the is and as in between the words. It sounds incredibly real, but these two people do not exist. And so now you can basically do this with anything you have. You can do it with your entire notes from your 4-year undergraduate course, from your high school. You can do it with our paper. You can do it with all the papers you can't be bothered reading. It'll turn it into a podcast, and you can just listen to the podcast. So then in the last 5 minutes, I was going to talk less about the application of medicine and a little bit about some of the ways we're also using these models in science. And this is a paper that came out yesterday. This is not from us, but I had to add it in since we're talking about things that are very up to date. This is from Cell, published yesterday. I've not read every word of the paper yet, but I did read the figures and the abstract and some of the other elements before putting it in. It's basically from Maria Zidnik at Harvard, and demonstrating how we could use AIs at all levels of scientific discovery, from brainstorming about an idea to thinking about causality, thinking about experimental planning. At the moment, the AI doesn't actually do the experiment for you. You've still got to do that. But then addressing the data, of course, analyzing the data, talking to you about the data, displaying the data, and eventually helping generate the paper. It's a pretty interesting read, and I think a way of which, as you can see from our work in the medicine field, the partnership between the human and the AI is, I think, going to be the most interesting thing. But I mentioned AlphaFold at the beginning. Of course, this has been a revolution in our ability to model proteins, and then in the most recent version, AlphaFold 3, our ability to model proteins and their interactions with other molecular entities, so like ions and nucleotides and other molecular entities. You can see some of them modeled there with the pictures on the right. A much harder problem, not as if protein folding wasn't a hard enough problem. And so this is pretty interesting, and I didn't manage to include a slide that one of my postdocs is working on, where we can basically model specific both mutated and non-mutated versions of the protein and their interactions, even with things like calcium ions, when I'm focused on the activation of the cardiomyocytes in the heart. So AlphaFold 3 and protein models in general, a big part of the future of drug discovery, and only getting better. Our most recent work has been in collaboration with this team based out of Stanford and the Arc Institute, thinking about scaling to DNA models. If we think about these language models and what they do, then we want them also to learn the language of life. So we know they can learn proteins. We've seen that with the Nobel Prize. It's a bit different when we think about DNA, and we heard this beautiful talk just a few moments ago about epigenetics. Think about the long-range effects of one piece of the genome on another and how it's all tightly compacted inside that nucleus. In order to do that with a language model, we need long context. We need to be able to understand the relationship between this word here and a word maybe a million base pairs away. And to do that actually cannot be done with the current models. So we've been working with these groups to try and think about long context modeling. The current model is called EVO. There's another model coming up. One of the applications of that would be to think about genome engineering and trying to help solve the delivery problem that we have. We have these great tools, CRISPR and base editing and prime editing, and we want to be able to get those editors to the right cell at the right place at the right time, but we're limited in how we do that. We've used adeno-associated viruses, but they have limited packaging capacity, and some of them, sure, go to the liver, but you try and get them to the brain and not the liver, or the heart and not the liver. That can be much harder. Maybe these models can help by designing new AAVs that are fine-tuned with data that we generate in our own lab, for example, from this human cardiac slice culture. And then we train the model with that knowledge, and then we ask it again to generate new capsid designs that will help us even more to emphasize the delivery to the heart and less to the liver. So just a quick example of that, there's also been novel CRISPRs that have been designed by some companies using a very similar approach. So I think the future looks quite bright for the possibility of applying these language models to the language of life. So in summary then, I have a few questions for us to think about. As you understand, I hope you would agree that we are really in the middle of a revolution that will affect all our lives as scientists and as doctors and beyond. Many of us are now using these models in place of search functionality for Google. They just give better answers. But there are some caveats to think about. Some of them are shown here. There are others. I know we'll discuss probably a few more on the panel later, so I won't go back to that. But I'll leave you just with this last bullet point and the question of safety in medical application of these, because of people having access to specialist care. Is an imperfect tool in the hands of many, many people around the world better than a perfect tool in the hands of only a few? I've shown you the work of many people. These are a few of them. Some of the people from my lab in my backyard, back garden, as I used to call it, backyard, as I now call it, I suppose. This is part of the team and some of our younger members of the lab shown at the front. Thanks again for the invitation. It was really a pleasure to be here, and I look forward to discussing later.
Thank you so much, Professor Elsley. Please be seated. Thank you very much. And next, we're happy to introduce with you Professor Catherine Shah. As this session's convener, Professor Shah is Emeritus Chair of the Biochemistry and Professor at the University of Hong Kong, member European Molecular Biology Organization, member Hong Kong Academy of Sciences, fellow World Academy of Sciences, member Program Committee of the Future Science Prize Week 2024. Let's give big hands to Professor Shah.
Thank you very much. I am really thrilled to be here and to be part of organizing this wonderful session in life science. We've heard already two absolutely brilliant talks from very basic developmental biology and underlying principles behind epigenetic and genetic inheritance to mind-blowing ideas about how AI is going to change medicine and our daily lives in the future. So the feast goes on in the following two talks, and the next talk is going to be delivered by Professor Lawrence Studer. And Professor Studer is a wonderful example of somebody who has achieved so much as a basic scientist and has gone all the way to clinical applications. Professor Studer is the director of the Center for Stem Cell Biology at the Sloan Memorial Sloan Kettering Cancer Center in New York City. He's a real pioneer in developing methods to differentiate human stem cells to neurons that can be used to treat neurodegenerative disorders such as Parkinson's disease. And he is also the one responsible for having a first-in-human clinical trial taking off-the-shelf stem cells, stem cell-derived neurons to treat a patient with advanced Parkinson's disease. So he has a wonderful background and wonderful research going on about how you can control differentiation of stem cells, not only to understand disease mechanisms, but for their application. So we look forward very much to his talk entitled Directing Cell Fate Developmental Time and Brain Repair Using Human Stem Cells. Welcome, Professor Studer.
Great. Thanks so much, Cassie, for this very kind introduction and for the invitation to be here. It's a pleasure to follow these beautiful talks about epigenetics and about AI with a talk about human pluripotent stem cells. And obviously notice that also the Future Science Prize winner of this year is Honghui Deng, who did beautiful work on the mechanisms of how you can actually reprogram cells back to pluripotent states using just chemicals. In fact, all the work that I'm going to show you has to do with human pluripotent stem cells. And before we get started, I just need to quickly, it moves forward on this screen, but not on this screen. Oh, no, it's coming. Let's go one more back. So just quickly my disclosures. And at least one of the disclosures, Blue Rock Therapeutics, which is a company that sponsors now some of the clinical work that I'm going to show you some examples at the end of my talk. Now, really, one of my major goals when I started off my career was really understanding how do you go from a pluripotent stem cells into all the cells of the human body. And there was really kind of a quest that might take decades to really figure out. But by now, at least for the nervous system, I think we have a very good understanding how to do that. So even if you give me any cell type of the brain or the PNS, I've never really tried to generate. I could use the same principles to get very close to generate those cells at high efficiency. And the way it's done is basically 3 major steps. And all those steps follow developmental biology. So step number 1 is you need to decide with regard to germ layer and subgerm layer identity. And so the amazing thing is actually to go from a pluripotent cell to a central nervous system cell is remarkably simple. So it turns it's actually a default in their development. So if you block all the signaling pathways, such as BMP and TGF-beta signaling, they spontaneously convert at nearly 100% efficiency into neural cells. If you don't play with just 2 more signaling pathways, you can now make all the major ectodermal lineages, not only the CNS, which is the brain and the spinal cord, but also the peripheral nervous system, the sensory structures, such as, for example, in your nose or in your inner ear, or also the skin. And so that gives you the first building block to specify those 4 major subectodermal lineages. But step number 2 is actually that for each of those tissues, there is something like a zip code. So it turns out the front of the brain, the forebrain, develops into very similar, very different structures than, for example, the spinal cord. And so what you need to instruct in a second step is not only making the right layer, but the right position in the body. And that's done by using so-called morphogens that pattern cells to those posterior fates, particularly so-called Wnt signals, and all the signals critical for that in an anterior-posterior, from the front to the back, and from the middle to the side dorsoventral position. So that's step number 2. And once you have the right tissue, the right position, the right zip code, you can predict which cell's going to come out from there. Then the final third step is really understanding timing of the process. Because in each of those regions, you actually have a sequence of events that happens from those cells born in this region. They make first neuron type number 1, for example, in the cortex, deep layer neurons, then they make upper layer neurons, then they make glial cells, and you can control the timing of that process with certain transcriptional networks, and you can force the cells to exit at step 1, 2, or 3. And so again, if you combine all those steps, you can do that either in 2D, making a layer of uniform cells, or you can also make that quite effectively now in 3D to make organoids in such a manner and to really build kind of an atlas of the nervous system. Many of you heard maybe of the idea of making a cell atlas using single-cell techniques, but the way we understand cell atlas is not only to profile the cells descriptively, but understand enough that we can actually generate them. And these are just one of those examples. By now we can make more than 50, it's actually more than 60 cell types routinely in a dish at high purity, at high efficiency, and use then the cells either for modeling a disease or, for example, using them as a tool for cell therapy. And so we really got good at this step, putting those 3 steps together into a logical manner. In fact, one thing is talking about AI is now saying, can we make that even more systematically and understanding basically even cell types we haven't really fully generated with that logic. Now, what we are not as good at is understanding time of the process. So it turns out when you go through those steps, they follow pretty much the human timing. And we all know to make a baby takes you 9 months. To then get to an adult stage takes about another 20 years. And to actually get age-related diseases, often they occur only when you're 50 or 60 years of age. And so this timeline is not really absolutely set in space, because we know in animals they can go through the same steps, but they can do it significantly faster. It turns out the specific factors, the signaling pathways, transcription factors that are important for those cell fate specifications are largely the same. But the way the movie runs, how quickly you go through the program, is actually very different across species. And so this is still one of the major mysteries that is a challenge in the field, because we want to use those cells to study adult or aged diseases. So we need to move the time clock forward to get to that late stage. So we worked on that also for quite a while, and we made some progress in the first step. How can you accelerate the time to go to initial fate? Can you go faster than nature? And we had such examples where we can screen for combinations of small molecules that can do the job slightly faster than normal development to make, for example, peripheral cortical neurons or glial cells in the brain. It still hasn't really explained with those mechanisms how we actually understand species-specific differences. And there's a number of groups that now have looked at that and found that there are actually species-specific differences between a mouse and a human in very fundamental processes such as protein degradation, transcription elongation, other biochemical reaction time or metabolic rates. And in some cases, they seem to roughly mimic the difference in timing between the developmental speed that basically cells go through these processes. Now, right now, most of that is still correlation and not causation, because it's very difficult to change protein degradation rate in a systematic way without really messing up whole development. Now, where actually the problem is even more acute is that we have not only a 2 to 3 time difference in going from pluripotency to a cell fate, but a much larger difference between a mouse and a human to go to a fully mature cell. So what do I mean by maturation? Maturation, I mean once we already specify the fate, you make, for example, a nerve cell in your cortex, for the cell to become fully mature takes a very long time in human compared to the mouse, at least a 10-fold difference. And so the question is, how do we understand that? And how do we model that? On the cell, because not a mouse cell, or in this case, a mouse, a pig, or a human cell, and graft them into an animal that has a depletion of that cell. And so now you're going to see over time, the grafted cells can take over the function that's lost in this animal model. And what you find is that the human cell takes much, much longer than the equivalent mouse cell These are so-called dopamine neurons in a model of Parkinson's disease. So even though they're in the exact same environment, they have a species-specific difference in their maturation rate to become mature enough to cure this animal from the dopamine deficit. And there's other work from, for example, Pierre van der Hegen, where he grafted mouse or human cortical neurons in a mouse cortex. And the human cell takes about 9 months for them to develop in these beautiful pyramidal neurons that if you show them to a pathologist, they tell you, okay, they look about like a neonatal cortical neuron. So meaning even though they are in a mouse brain that develops much faster, they stick to their human speed. And so there's a little bit of work, again, that suggests that, for example, the energy metabolism might be involved in that. So again, work from Pierre van der Hegen showed that if you enhance mitochondrial maturation rates, you can somewhat speed up the process, but it's only a very partial success. What we try to do is, one approach is just simply, can we screen for factors that can accelerate it? So in this case, we developed a chemical screen where you first make the neuron very, very precisely. All neurons are born at the same time. Then you expose them to a large number of chemicals. You wash out the chemicals, grow the cells for another week, and you ask yourself after an additional week without any such treatment, do they remember the previous treatment? And they found, in fact, that 4 such molecules could do that in combination we refer to as a cocktail called gin tonic. You can imagine the student liked to have gin tonic drinks, but it comes really from the letters of those molecules. Now, the way it works seems to be that you actually have to inhibit, we talked about epigenetics before, something which we are referring to as an epigenetic barrier that in human actually resolves extremely slowly to allow maturation to occur at the right speed. And then you have a second set of activity-dependent programs that come in neurons. And once they basically become fully active, trigger activation-dependent maturation. That's, for example, the maturation program that you have in a baby once it's born. You start seeing your eye put model system, or you can do it also in 3D organoids, where you can now get significantly more synapses formed much, much earlier with this gin tonic cocktail, and you get much more early spontaneous activity. Now, when you look at that more systematically, what is really fundamentally happen as the molecular substrate of maturation, Gabriele Ciceri in the lab is a postdoc who really established the atlas of maturation at the level of function, at the level of molecular states, to then map, for example, what happens transcriptionally, moving from a very early pluripotent cell all the way to a young neuron to a more mature neuron, and how can that reflect the maturation that happens normally in the brain, and how we can stage them with regard to their age. We can then look and define the transcriptional programs that are underlying that by looking at the chromatin in those cells. But what was most intriguing is what we found is actually the gene regulatory network that very, very slowly decreases during maturation. And it turns out that most of those factors were, again, these chromatin-related barrier factors that were most highly enriched. And in fact, we found more than 30 such factors that are expressed in young neurons when they are born that very, very slowly get downregulated over a period of many, many months. And it turns out about half of them, if we just simply overexpress those, we can achieve an acceleration either in marker expression or in the activity of those neurons. And what's quite remarkable for those factors is that nearly all of them seem to be retained in individual neurons. So what I show you here is a single-cell data set from the developing mouse brain. And we basically use a tool to just look at gene expression once the cell is becoming a neuron. So this is purely maturation process at this stage. And we look again at our maturation factor that came out of our atlas, and we found in all those neurons, independent which neuron they are, this barrier has to go down over time to allow for the maturation to occur. When we then look where do those factors come from in development, we find that they actually expressed even much earlier than when the cell becomes a neuron. And we can actually now go ahead and inhibit those factors already at the stage when a cell is still a precursor cell, just at the transition to become a neuron. So in this case, you inhibit those epigenetic regulators such as PRC2, which is a polycomb-related epigenetic regulator. We can inhibit those just transiently in the neuroprecursor stage, take away those chemicals, let the cells allow into neurons, and now the neurons mature more quickly. That's shown with this maturation scoring factor. For cells, again, they were treated over here outside of the graph, but the cells remembered that treatment and now mature more quickly, a little bit more akin what you see in a faster developing species, such as in a mouse. You can again measure that in many different levels. You can look at excitability, synaptic connectivity, activity in those organoids, for example, again, can be done in 2D and 3D, and all those factors respond in a similar way to now show that just simply by inhibiting those transiently this barrier, we can get a faster maturation occurring that seems to persist. Now, I don't go too much into the mechanism, because obviously it's a quite complex underlying mechanism with regard to the factors that contribute to this epigenetic barrier. One of the most powerful factors among those was, again, factors that inhibit this PRC2 complex, these EZH2 inhibitors. And so we then asked mechanistically, so what does that mean for maturation? We had a beautiful introduction about epigenetics, about DNA methylation, but also about histone modifications. And PRC2 is particularly important for one of those histone modifications called HDK27 trimethylation, which is an inhibitory such modification. So what we did here is we just simply looked in young neurons, or in more mature neurons, or in precursor in neurons, what distinguishes basically this chromatin signature in the cells, and which of those chromatin patterns on a set of genes, so this is a set of genes that has this specific pattern, another set of genes that is deposited chromatin with this specific pattern, and so forth. So you want to know which of those patterns actually correlated with maturation. That's shown here. So these are genes here that show this maturation-dependent expression pattern, so they increase. And we found that these are particular genes that have a so-called bivalent state, where they are ready for activation, but they don't really show you a gene expression. And that seems to be one of those barriers that needs to be removed when a neuron wants to fully mature at a certain speed. And so we showed that indeed we can then inhibit those PRC2 component factors, we inhibit those specific inhibitory factors, and show that indeed we, for example, affect this deposition of HDK27 at the genes important for the maturation process. So the summary of this part is then really that we have now, I think for the first time, a good way to understand why do human cells go so slow. And maybe, if you say, why has nature designed it like that, it's maybe quite obvious. The brain is extremely complex. You have 100 billion neurons, and they have to be all born over a certain amount of time. They have to connect with each other under those conditions, and it doesn't make sense now to make them super fast before they are even ready to properly connect. So it's like a symphony of factors that has to go in the right sequence and events to actually achieve the enormous complexity of the human brain. And again, we have now at least some glimpses of how that works, how we can inhibit this barrier either in the neurons or already in the precursors. And we know other components that contribute what's called in gene regulatory network is epistatic interactions of what you can actually inhibit and what is required for the inhibition to trigger a maturation program. Now coming back to the mouse and the human, if you actually look, so is this program in any way different in a mouse or in a human? It's clearly not going to be the only difference between species, but we can actually use methods of single molecule counting of component of the epigenetic barrier, shown here, like EZH2. And what we find is actually that the human has equivalent, at the equivalent stage, is a higher barrier than the mouse. So this is a very primitive way to show it, but might in part explain again why it's much more difficult to get this barrier to decrease over time in a human cell than in a mouse cell. And conversely, you can now actually do the opposite, and basically with that knowledge engineer mouse cells that now for example, develop slower, more human-like. And so this gives you, again, kind of a glimpse of some of the changes that we can use to control timing in our human stem cell system. And there are many other projects ongoing, for example, in the lab. For example, one idea that's even more radical is that you can now fuse human cells with mouse neurons and see, do they now go at the speed of a mouse or at the speed of a human, which was actually a very critical experiment pre-Yamanaka, figuring out that all the factors that can induce pluripotency are present in an embryonic stem cell. And in this case, we actually have now evidence that indeed we can accelerate human timing in these hybrid neurons. And we have also another story, which maybe soon comes out, where we did genome-wide CRISPR screen and again came across this epigenetic barrier as a key component of the timing factor. And then the final part really of the timing question is, we don't really just want to make mature neurons, but we also want to understand aging, what controls aging, and maybe what we can do to reverse it eventually. And so in this case, we have just recently published some of the criteria how you, at the cellular level, do you actually know that you have an aged cell or you have a young cell. And these are some of the key factors that distinguish those cells, and some of the manipulations that we and others have published previously try to induce an age-like state. And just very recently, we've performed a genetic screen that found a new player in this pathway, which is called protein nedylation. It's a pathway that's very important, interacting with another protein degradation pathway in boosting degradation of proteins at a certain time point. I mentioned your protein degradation is very important for timing. And in this case, we can actually just add a drug transiently to certain neurons that have a mutation in either Alzheimer's gene or in a Parkinson's gene. And if you do that in a young neuron, you can measure the changes related to that mutation. For example, they have more of this Alzheimer protein called A-beta, but they don't degenerate. But if you now do the second step, you inhibit the nedylation, you trigger an aging program in the cell, and you can actually, for the first time now, get reliably see the tau phenotypes and the degeneration phenotype in those systems. And it works beautifully for both modeling Alzheimer's disease, which was shown in this study, but also actually for modeling Parkinson's disease, where you get only in a genetic context the combination of the genetic vulnerability and the age of the cell converge into triggering and modeling degeneration. Now, having talked about Parkinson's disease, that's really then the other approach how you can use stem cells, not only making the right cell, the right genetic modification to model the disease, but using the cells for the actual therapy. And so this is an attractive approach in Parkinson's, because it turns out all the classic motor symptoms of Parkinson's disease are caused by the loss of a very specific population called midbrain dopamine neurons. And I mentioned to you before that the brain, human brain, is about 100 billion neurons, but it turns out dopamine neurons are about only 300,000 to 400,000. So it's a very rare population of cells. And once you lose about half of those, you start getting symptoms of the disease. So therefore was the idea, if you know that those cells are lost, they are the cause of the symptoms, can you just simply put a few 100,000 cells back and rescue those symptoms? Now it's important to understand that Parkinson's is not just a dopamine neuron disease. There are other symptoms as well, for example, problems in sleep, in the gastrointestinal tract, in the context of smell, and even at later stages, cognitive dysfunction. And so those symptoms are likely not going to be affected by dopamine grafting. So what currently we try to do in a most positive way, we try to cure the movement disorder of Parkinson's disease, but we might not truly cure Parkinson's disease with regard to the other symptoms. Now, this idea has been around for a long time. It was actually done first, even when I was back in Europe, very involved in some of those trials, using fetal transplantation, where dopamine neurons were plucked out of a developing fetus and then grafted into patients. And what we learned from those studies is that the cells can survive in a Parkinson's brain. They can actually survive for up to 25 years, which is quite remarkable, 24 years without any immunosuppression. The problem really with fetal tissue was it was very difficult to procure, highly variable, and placebo-controlled studies didn't really show a consistent effect, in part because it was so difficult to design consistent trials. Nevertheless, some of those patients were followed for more than 15 years, and some of them Admittedly, a small subset of them showed remarkable effects, meaning they actually had, for example, completely could stop their L-DOPA therapy, which is the most common therapy that these patients currently get. So this was quite remarkable and suggests that this could work. But on the other hand, it might never really work properly with fetal tissue. And this is a paper that's soon going to come out from our colleague of ours, Roger Parker, that went actually back and tried with our knowledge now, 20 or 30 years before these initial studies were done, can we go back to fetal tissue and do it better? And as you will see, if you read this paper coming out soon, there's still a lot of problems with that. Even with today's knowledge, fetal tissue is too variable, too difficult to procure and standardize. And so that was really my vision when I started actually going to the US at the time, that we need to have a stem cell source to really achieve that. And it took us about 10 years of work to figuring out the developmental biology to make the right dopamine neurons. I'm not going to go into details of that, but it's a cell that can survive in a mouse, rat, or monkey model of Parkinson's disease. These are models, very simple ones, like this rotation model. This is obviously a sped-up movie, but it's an animal that's lesion on one side of the brain, has no dopamine on one side, and once it's grafted, it becomes symmetric. There's another animal cannot really properly initiate movement with the left paw. It's not paralyzed. It's not like you have a spinal cord injury. It can move it, but it cannot initiate movement, which is exactly what happens for a Parkinson's patient. When, for example, a Parkinson's patient wants to move across the street, the light turns green. They always have a long time before they can actually initiate movements. Then they have shuffling movements to move forward. So that's what happens here. So the animal drags the paw, but then 2 or 3 months later, it can again put weight and properly move the paw. When we graft our dopamine neurons, we also know exactly how those neurons work. So it's not just a black box, putting them in and the animal goes better, but you can actually do so-called optogenetic studies, where we take the same dopamine neurons, but we put in like a light switch. So you can now graft the neurons, but you can now shine light on the brain, and when you shine light, just during that time, the nerve cell shuts off. And if you do that, within a minute, all the benefit you have from the animal, from the grafting, goes away. We can also show that once the activity goes away, that it's activity dopamine release that causes the benefit. And what's shown here is even more sophisticated. That's what the neuroscientists do. They actually stimulate certain nerve cells in the region of the brain, the cortex and thalamus. They record from these blue and red neurons in the striatum. And these are the neurons, the circuit that's modulated by dopamine. And you can show exactly when you switch on the light, that the strength of the synapse drops. When the light is off, it goes back to the normal strength. So what that means is these dopamine neurons work exactly the way normal dopamine neurons are supposed to do. With these basic insights, we then worked for nearly another 10 years, getting all the regulatory approvals to move these cells to the clinic. We had to do extensive preclinical studies in hundreds of animals, in rats and in monkeys. I'm not going to bore you with those studies, but just one example to show you for the efficacy, how it works, is you have this lesioned animal, so lost dopamine on one side of the brain, and after grafting, you see it's, again, pretty much fully symmetric. And this rotation movement that I showed you before in the video, from 10 rotation, goes back to 0. So this led then in 2011 to the first time that we were allowed to use these off-the-shelf dopamine neurons. We made billions of those neurons in hundreds of vials to be ready for grafting. We did that in New York in MRI-guided OR, where you can very precisely deliver the cells at the right site. You do this implantation at 3 different tracks, 3 different deposits in each track on both sides. And you can then see actually the tracks right after grafting. So this trial basically involved 12 patients. They are now all grafted, and they're all at least 2 years after initial treatment. 5 patients were at the lower dose, and 7 patients at the higher dose of treatment. And we had also exclusion criteria. Again, if these patients have, for example, dementia or other issues, they were not included. Now, this is a phase 1 study, so the most important thing you have to report is safety. And indeed, we had excellent safety, so we had no therapy-related adverse events. And we had also no of the side effects that were observed with some of the fetal grafting in the past, because again, we can much more precisely shape the cells and avoid the cells that we think caused the graft-induced dyskinesia in the past. We then can show that the graft actually survives and functions. So this so-called PET imaging, where you have a dopamine tracer, this is pre-treatment. And you can say usually this dopamine signal that's a PD patient gets weaker every year, but in fact after transplantation bilaterally, it gets stronger over time, and it gets stronger even after the time we, for example, remove immunosuppression in those patients. And again, I don't have time to go through all the clinical scores. I'm just going to show you one example of a clinical score now at 2 years of time, which is the so-called UPDRS score. This is a score where patients are rated by motor function. And once you have about 40 to 50 points, you have pretty severe Parkinson's disease. Every year you look at initial 2 to 3 points, you get worse. And when you get about 5 points difference, that's really clinically meaningful. And what we found is, particularly in the high-dose group, is that the patients drop by more than 20 points. So that's more than 4 times of what's clinically meaningful. And so we were very, very excited. In fact, we saw an effect that maybe was even better than what we dreamed of when we started with regard to that. And we also could avoid some of the side effects. This is what's called the graft-induced dyskinesia. So therefore, we seem to have a very promising strategy. Now, again, obviously, it's still early stage, but we know that we can deliver the cells safely. This is the first off-the-shelf dopamine product in the field, so it could be scaled potentially to many, many patients. We have evidence that there's a dose dependency. We can avoid some of the side effects that have hindered this approach in the past, but obviously we have only a small number of patients so far. And so what really needs to be done now is to scale that up to a larger study that is starting in 2025, which we hope there could be an actual registration trial. Just the last minute, we also think obviously what's next. On the one hand, we can still even make these cells even more precise than in the past. So it turns out they're not only dopamine neurons, but the different subtypes of dopamine neurons. And we have now very good understanding, much better than when we started the clinical trial, of how to make those cells using single-cell approaches, basically intelligent design, and then making selectively just one versus the other dopamine neuron subtype. We understand better what's the limiting factor in these cells to survive in vivo. And finally, we can also endow these cells with additional factors to either completely avoid even the transient need for immunosuppression, or to protect them from the ongoing disease that might affect these cells, we estimate maybe after 10 or 20 years after. And just for this one, we just had a paper earlier this year to show that we actually now understand what limits the survival of these cells, where with a CRISPR screen that identified p53 as the culprit of a neuronal death response when we graft. So typically, about 5 to 10% of the neurons actually survive, 90% die. The way we solve that clinic is we just graft more cells. But we obviously want to know what is really the mechanism behind it. And we found that this is actually TNF-alpha that's triggered this response, and we can use commercial TNF-alpha inhibitors to prevent this response. We also know that it's actually graft-derived TNF-alpha, so there's some interesting mechanism of how that intersects and triggers this p53 response. And then finally, we can put all this together and now graft not only our early, relatively first-generation product, which are dopamine precursor young neurons, into making highly precise dopamine neurons and subtypes, and getting those to survive reliably in animal models of disease, to maybe be the second or third-generation product that ultimately should help the patients. And last but not least, I want to just quickly mention some of the key people of the work who are important for the maturation work. Emiliano, Andrew, and Gabriele, with the paper just published earlier this year. Natalie, and then the larger team, including my colleagues at Blue Rock, and a partner over many years, Dr. Tebar, who was doing most of the surgery in those 12 patients today. And we're going to stop here and hope we'll have later an interesting discussion. Thanks so much.
Thank you, Lawrence, for a truly inspiring lecture to help us to see the relevance of developmental biology all the way to treatment in patients. We continue our journey now with more exciting talks from Professor Hai-Fin Lin. Hai-Fan is the Eugene Higgins Professor of Cell Biology at Yale University. He's a member of the National Academy of Sciences of the USA and American Academy of Arts and Sciences, and also a foreign member of the Chinese Academy of Medicine, Chinese Academy of Sciences. Haifan is a pioneer in stem cell biology and cell biology, and discovered a very unique category of genes called the Peewee genes, which I think he's going to talk about today. And this was a fundamentally really an important discovery, which was cited to be one of the 10 most exciting discoveries of the year when he produces. He's also a very big leader in many organizations, and in particular in stem cells, as the just past president of the International Society for Stem Cell Biology. And today we are in very good company, because Lawrence will be the president-elect in a couple of years' time. So we have a very good representation of stem cell biologists here, and so we welcome Haifan very much for your lecture.
Well, Catherine, thank you very much for your kind introduction. I wish my mother's to hear this introduction. I first of all like to take this opportunity to congratulate all the recipients of this year's Future Prize. Their groundbreaking discoveries epitomizes what's called original and impactful research. And as you've heard from Kathy's introduction, I'll be talking about our own discoveries related to stem cells. And as you probably know from Lawrence's talk, and we'll be hearing from this year's recipient, Dr. Hong Kwek Deng's talk, stem cell research represents a very exciting frontier of biomedical research, promise to cure diseases and regenerate organs in our tissues. However, I want to tell you about our own work, the discovery of a new paradigm of gene expression from our stem cell work. So when you think about stem cells, you often cannot help but relate these two words to longevity and immortality. And this actually, the pursuit of immortality has been a long pursuit in human history ever since the dawn of civilization. For example, more than 2,300 years ago, Emperor Qin, after uniting China, his next pursuit was to pursue a magic potion that will make him live forever. He ordered the alchemist Shifu, who led an impressive fleet of 3,000 young men and women sailing towards the mystic islands in the east, where Shifu claimed to have these magic potions. The fleet disappeared in the ocean, and later a small island country called Japan appeared, but Emperor Qin never got the magic herb. He died at the middle age of 49, and we started stem cell research just a little bit too late to save his life. Today, we know that there's no such a thing called the magic potion that can make you live forever. However, stem cells are perhaps the closest things that we have in real life. Then what are stem cells? So Lawrence already shown you that stem cells can generate neurons, but let me just take one step back by showing you that totally in our bodies, there are two types of stem cells. Embryonic stem cells that exist in our early embryos, they can generate all types of tissues and cells in our bodies. And the second type is called adult stem cells or tissue stem cells. They usually can only generate differentiated cells within their residing tissues. For example, neural stem cells can only give rise to neuron and other accessory cells, but not pancreas or bone, for example. Despite the big difference between these two types of stem cells in their pluripotency versus multipotency, they have a common property, namely they all have the ability to renew themselves. Therefore, these cells are viewed as the fountain of youth that can provide so-called endless supplies to body's tissues, at least during our lifespan. Now, then the question becomes, what makes these cells to have this amazing ability to self-renew? people have been looking for genes that controls their behavior. And more than 20 years ago, my lab discovered a gene family called the Argonaute PV gene family that turned out is essential for stem cell renewal in both animal and plant kingdoms. So we started this work by using little fruit flies, Drosophila, as a model. And as you can see, this little fruit fly has a very powerful, been a powerful model for genetic studies for over a century. Many of the important genetic laws and genes that applies to clinical applications today are actually initially discovered in these little flies. So we thought these little flies could be also a great model for stem cell research. We decided to focus on the ovary of the flies because it contains a small number of actively dividing germline stem cells that can produce many, many eggs throughout the lifetime of the fly. So shown here is a normal ovarian unit in the fly. You can see the two germline stem cells here have undergone many self-renewing divisions to produce a long string of developing egg chambers, which are all colored in brown here. Now, if you knock out a gene called PV in Drosophila, then these two stem cells will just self-differentiate into two egg chambers, but no longer can self-renew to produce more egg chambers. So this phenotype showed clearly to us that this PV gene is essential for the self-renewing division of stem cells. And we showed that this function actually is highly conserved throughout the evolution. For example, in mammalian system, if you look into the testis, this is a structure of testis called the seminiferous tubules, which is a site of sperm production. You can see there are a number of stem cells sitting there. By now, in this young mouse, they have produced many differentiating germ cells and eventually many mature sperm. However, if you knock out a PV gene in mouse, in this case called the mouse PV-like, or MILI for short, you can see these stem cells will still be there. Let me just orient you with these stem cell daughter cells and sperm here. But however, these stem cells will be just sitting there and doing nothing. So therefore, this testis tubule that's actually shown in the mutant under the same magnification as in the wild type appear to be much smaller and contain only the inactive stem cells. So then what's the structure of this family of genes? This family of genes actually encodes a protein that contains 4 functional domains: the N-terminal domain, the central PAG and PV domain that together can bind to small RNAs, and also a C-terminal domain that resembles RNase H. That means this domain may have RNase or even nucleic acid cleavage activity. And here is a 3-dimensional structure of these proteins. As you can see, the PAG and mid-domain together form a cleft that can hold these small RNAs. So we then further divided this protein family into Argonaute and the PV subfamilies. As many of you probably know, that the Argonaute subfamily proteins, they are central engines of the RNAi and microRNA pathways. They bind to siRNA and microRNAs, and they are always about 21 nucleotides long. And both the Argonaute proteins and these small RNAs are expressed in most cell types. Therefore, today, RNAi and microRNA pathways work in most cell types. And I was very delighted to learn that 2 friends of mine, Victor Ambrose and Gary Rufkins, they received the Nobel Prize last month for their work on microRNAs, in addition to the Nobel Prize given to the siRNA work several years ago to Andy Fire and Craig Melrose. My lab have actually been focusing on the PV subfamily because these subfamily proteins are mostly only expressed in the germline and primitive stem cells. About more than 10 years ago, as Kathy mentioned, my lab and a few other labs discovered yet a new class of small RNAs that we named PV interacting RNAs, or pRNA for short, that are bound by these PV subfamily proteins. And just like PV proteins, these RNAs are also expressed specifically only in the germline and stem cells. The next slide will show you a brief comparison of the salient features between the pRNA and microRNAs. As you can see, pRNA is a bit longer than microRNA. In addition, pRNAs are much more complex than microRNAs. So today my lab has cloned more than 20 million of pRNAs, which is more than 700 times greater than the total known number of genes in our genome, which is in sharp contrast to the about 1,000 species of microRNAs that we discovered so far. Now, in addition to this complexity, these pRNAs are also amazing in that they correspond to all types of genomic sequences, which again is in contrast to microRNAs, which only target the 3' UTR of mature mRNAs. So of course, the biogenesis has to be different. pRNAs are mostly produced from very long single-stranded RNA precursors, in contrast to microRNAs that are produced from hairpin structures. So we were very excited about these discoveries because if you think about the grand scheme for molecular biology research in the past 6 decades, the research has been focused on the central dogma, which tells us that the genetic DNA is transcribed into messenger RNA, junk DNA. So little about these regions in our genome. And what we found is that most of the genes that encoding the pRNAs are actually hiding in these so-called junk DNA region. That make ACE. And this was a pie I baked for my lab to celebrate the discovery of pRNA, rhesus pRNA. And as you can see from the trembling hand here, you can tell how excited I was when this was found. So, and as Kathy mentioned, this discovery was selected by Science as one of the 10 breakthroughs that year. All these hooplas aside, an essential question remains: so what's the function of these pRNAs? So today I'd like to show you these pRNAs have 2 important functions. One is when they and the PV proteins are in the nucleus, they play a very important role in epigenetic regulation. And when we talk about epigenetic regulation, I'd like to thank Professor Ann Ferguson-Smith, who has articulated so beautifully about what's epigenetic regulation to you. So let me just briefly recap. Epigenetic regulation refers to heritable changes in genetic information without changing the DNA sequence that eventually leads to the programming of cell fate and to create an organism with diverse cell fate and multiple cell types. Epigenetic regulation, obviously today have been focused on identifying epigenetic factors and illustrating how they modify protein and DNA modification status, just as Anne showed earlier too. Those epigenetic factors can methylate DNA, or in this case, I'm showing some epigenetic factors. They can possibly do other things, like HP1 means heterochromatin protein combined to the histone associated DNA to make that part of the genome become heterochromatin. Now, if you think about these important factors, one question actually begs for answer, which is most of these epigenetic factors, they're actually just enzymes. They do not bind to DNA, let alone have DNA recognition ability. For example, HP1 doesn't really directly bind to DNA, and histone methyltransferase doesn't really directly bind to DNA in a sequence-specific fashion either. So then to me, a central question in epigenetics that need to be answered is how these epigenetic factors are guided to specific sites in the genome in the right type of cells at the right time. For example, guided to here, but not here or here. So today I hope to tell you that PV RNA pathway actually play a major role in this process, at least in reproductive cells. So when we started our work, a few transcriptional factors were shown to be able to recruit a few epigenetic factors to the promoters of several genes. And that is an exciting first step. But to me, it reflects more an exception than a norm in the genome, because truly there are only a few genes were shown at that time for this kind of guidance. And also, it's a feedback mechanism. So we decided to look into whether PV proteins have an epigenetic role because it was present in the nucleus. And when you do genetic analysis, it shows all kinds of phenotypes that qualify to be epigenetic factor. And here is a very visually clear cytological analysis to show you that in the Drosophila polyethylene chromosomes, which are standing in red here, PV protein, which is in blue, green here, actually can directly bind to many sites in the genome. Now, if you further this analysis to molecular level, shows the Drosophila genome here with the telomere of X chromosome here and the centromere here, as well as the left and right arms of second chromosome and the left and right arms of third chromosomes here. You can see when you map RNAs, this is 14,000-ish PV-associated RNAs that we first discovered in fly. You see these little peaks. Each peak represents an individual RNA. They are there scattered throughout the entire genome in all kinds of genomic sequences. Especially they are in the pericentromeric heterochromatin, and they're also enriched in telomeric heterochromatin. Of course, they're also there in many euchromatic sites. So our study in the past 10 years or more allowed us to show that these RNAs and PV proteins together, they can form a formidable guiding mechanism to pull epigenetic factors to many sites in the genome. So using, again, here one particular PV protein called mu in mouse as an example. Now, in mouse germ cells, the RNA coding gene will produce a very long single-stranded RNA precursor, which will then be chopped by the mouse PV protein called MIV2, means mouse PV number 2, that's localized in the nucleus. And this protein's nucleus activity will chop the precursors to produce mature RNAs. And the mature RNAs will be bound by this MIV2 protein to form many RNA MIV2 complexes. And these RNA MIV2 complexes then will target genomes with the complementary sequences. For example, this green RNA here, we're targeting this particular gene called the RAS-GRF1 that contains a green RNA complementary sequence, which is colored in green here. And that will lead to the recruitment of the PV RNA complex specifically to this locus by targeting the nascent transcript that's still tethered to the pol 2. And that will then further lead to the recruitment of DNA methylases to this site. And that will lead to the site-specific methylation at this locus. And as you know, that site-specific methylation, again, as Han has illustrated to you, is a very important form of the epigenetic regulation, and that will contribute to the definition of these cells into the stem cell fate. So now, if you look into this question again, what I hope to have shown you today is that we actually have discovered a major mechanism that can guide epigenetic factor to their target site in the germline genome and in other cell types that have RNAs. However, when we looked into all the PV proteins, not all PV proteins are in the nucleus. For example, this PV protein in mice called MIV2, means mouse PV, actually is in the cytoplasm. So this is the seminiferous tubule of a juvenile mouse testis, now standing in green for laminin to outline the tubule itself, and the MIV protein is standing red. As you can see, MIV protein is present only in the cytoplasm. Then what's the function of the PV RNA complex in the cytoplasm? It turned out they have a second very important function, which is to have a post-translational regulation effect throughout the entire genome. To address this question, let's again go back to our genome. Our genome contains 23,000 genes. In addition, there's a vast intergenic region in which many transposons reside. For example, in mice and humans, we have 1 million transposons residing in our genome. As Anne told you, that's about 40% of the entire genome sequence. And 96% of these transposons, they're actually radial transposons, they make intermediate RNAs in order to jump. And in addition, more recently, my lab and others have found that there are many other genes also in the genome, in addition to the protein coding genes and transposons, which are mostly viewed still as selfish parasites that invaded our genome that we had to cope with. Now, these other new genes encoding the linker RNA coding genes that produce tens of thousands of linker RNAs, and the piRNA coding genes that produce tens of millions of piRNAs. We should not forget that our genome also contains a large number of pseudogenes. For example, the human genome contains 35,000 pseudogenes. Most of those pseudogenes can be transcribed into RNAs, but because the open reading frame is mutated, these RNAs cannot be further translated into proteins. And these pseudogenes are often viewed as a defunct carcass of our active genes on their way out during evolution. Now, despite the conspicuous presence of these genomic elements, we still should remember in our genome there are sequences which are important structurally for cell division and for chromatin maintenance, namely centromeres and telomeres. So in the past couple of years, my lab discovered that even centromeres are made into RNAs. They're called satellite RNAs. Now, we call all these different types of genes and sequencing genome as different constituents. So our genome is not just made of 23,000 genes, but millions of these kind of different constituents. And despite their presence, very little is known about their functional or regulatory relationship. So in the past few years, we've shown that actually the transposable element can play a very active role to regulate the expression of many protein coding genes at the post-transcriptional level. In addition, we showed that pseudogenes can also regulate the expression of the cognate sister genes. Furthermore, we showed that transposons can also regulate the expression of many linker RNAs. And now, most recently, we showed that all these regulations are mediated by piRNA pathway, including the functional piRNA pathway in regulating the centromere function during cell division by regulating their product RNA, namely satellite RNAs. So how are these regulations achieved? It's actually achieved through this process. Let's go back to the central dogma again. So the central dogma tells us that a gene is transcribed into messenger RNA in its precursor form, which is then capped and tailed and then spliced to become mature messenger RNA, and then got exported into the cytoplasm. However, we found that in germ cells and many other cell types, transposons are actually also expressed, even though at a low level. And these transposon pro-RNAs will be processed into piRNAs, which are then bound by PV proteins to form PV piRNA complex, which will then allow this complex to target those messenger RNAs which contain transposable elements in the 3' UTR of their sequences. You feel like many people have studied our transcriptome, and tens of thousands of labs have looked into messenger RNAs closely. But it's interesting that very few reports, if any, have reported that messenger RNAs actually contain transposable elements. And we actually found that in the mouse genome, 37% of genes have their messenger RNAs containing transposable elements. So just for young scientists in the audience, this study taught me a big lesson. Even if you're doing genomic study, you still follow the conventional wisdom that cell biologists often say that you only find what you are looking for. You have to ask the right question. And so we found that come to human, amazingly, the number of genes that contain transposable element in the 3' UTR now increased to 50%. Means 1 out of every 2 genes in our genome actually has transposable element bits and pieces in the 3' UTR. We have no idea how these elements get into the protein coding genes, but we do know they play a very important function. And now we should be also cognizant of the fact that the pseudogenes are often transcribed, and they will make RNAs that will be further processed into pRNAs, and the pRNA will be bound by PV proteins to form this PV pRNA complex containing pseudogene antisense pRNAs that will be against the sister gene throughout its entire length. And this is how, in reality, in the most important type of cells, germ cells in our body, how gene regulation is happening, not just a central dogma. And this also is true for the regulation of non-coding RNAs. When linker RNAs are expressed, we found that at least 30% of linker RNAs contain transposable elements. And these linker RNAs then become the subject of regulation for these pRNAs that are regulated by, produced by transposons. And through that, they actively regulate the linker RNA pathway. So just to summarize my talk today, I've shown you that, first of all, if you liken our genome as a world, in the old world, we should not only remember that we have 23,000 traditional genes. Our old world also contains many pseudogenes and many transposons. And now many labs, including my labs, our work have shown that there's a completely new world that exists in our genome, and this world contains many genes that are encoding for pRNAs, for linker RNAs, and for other type of non-coding RNAs. And recent work in my lab has shown that these two worlds are actually closely interacted and closely connected. For example, pRNA genes can regulate the expression of traditional genes. pRNA genes can regulate the expression of linker RNAs, and even the transposons can regulate the expression of traditional genes, and even the pseudogenes can regulate the expression of their sister active genes. And finally, pRNA pathway can even regulate the function of centromere and telomeres to maintain the genome integrity during cell division. So I'd like to acknowledge many former and current lab members who contribute greatly to the discovery that I covered in my talk, and especially these three individuals, Hang Yin, Toshi Watanabe, and Niels Nicholson. They made major contributions to the discoveries I talked today. I'd like to stop here, and thank you very much for your attention.
Thank you so much, Professor Lin. Please stay with us. And could you please proceed to another side of the stage? Thank you very much. Yeah, I can stay with you. Yeah. Maybe we can stay another way. Then they can have more, for the arrangement. And just in our keynote session, speakers explore the groundbreaking research shaping the future of human biology and health. Topics include the significance of epigenetics, AI's role in biomedical advancement, stem cell applications for brain repair, and genetic regulation via the PV RNA pathway. While we are doing the preparation, you may find a robotic arm just over there at the foyer area. Actually, it's for creating the Chinese traditional ink style portrait through the AI technology. So let's have a try today or tomorrow. And then now we're going to move to the panel discussion. May I invite our moderators, Professor Tongdu Mok, and also Professor Catherine Xie, and our panelists, including Professor Yuan Ashley, Professor Anne Ferguson-Smith, Professor Lin Haifan, and also Professor Lawrence Judah. So I may pass the stage to our moderators. Thank you.
Thank you so much. With such an excellent talk, I'm sure we got a lot of questions. Why don't I kick off with one? And then if anyone among the audience would like to entertain your question as well. I start with a tough one, Yuan, an AI question. Now, you just mentioned that AI may have a mind, but when there's a mind, the mind can lie, or the mind can learn the wrong thing if the data is wrong. So when I get something generated from AI, how can I know if they're lying to us, whether it's the correct data? How can we deal with this information? In a sense, is that how much can we trust the AI?
Yeah, it's a really great question. I mean, I think that the veracity of data is an issue wherever it comes from. And so wherever on the internet you find it, even if it's a Google search or a Bard search or Baidu search, then you still have to decide whether you trust the data. So wherever the data comes from, you need to apply your human brain towards it. It's a bigger challenge with language models because essentially, as we discussed a little bit ago, they're next token predictors. They basically are making a probability guess as the most likely word from all of their training data that would come next. So they're not directly connected to truth or to knowledge in that way. But you can directly connect them to knowledge or truth in a couple of different ways. One I discussed on our slide, this RAG model approach where you take retrieval augmentation. So as well as next token predictions, you also can have the model go to the internet or to some other trusted source and pull back specific data, specific facts, and have it surface that. And they've been shown time and again, that approach has been shown time and again to be more accurate and to help with this hallucination issue. I think the other is that there are certain questions that you could just imagine a next token prediction will never it's just not equipped to answer. For example, how far is it from Beijing to Tokyo? I mean, the language model isn't going to give you an accurate answer to that because you need a model of the world and it needs to be geographical. But there are plugins, for example, there's one from Wolfram Alpha that you can go to that does have a map of the world and that is able to measure things in it. So again, I think we're augmenting the language model prediction with facts about the world. So that's some part of an answer. I think hopefully the example I gave from GPT 3.5 to 4, where it was essentially not recognizing an important medical condition, and then the next version did recognize and give the appropriate advice, I think should give us all hope that we are making progress, but it's still a really important point, and it's not fully solved by any means. Thank you.
So would the others like to make a comment about AI?
Well, I am a very positive person, and I feel AI definitely is, like a flood flooding into our field, but it's a good flood, and we are opening our arms to embrace this. And in my lab, we also have studied AI approach, but definitely not to your level. We are beginners.
Can I ask a question actually about the difference between, you used that really nice example of the deep vein thrombosis, which is a very striking example. What was it between the two algorithms that made that difference to go from being quite wrong to being more correct?
Yeah, so they haven't I mean, of course, there are lots of examples like it. The difference between 3.5 and 4, as it turns out, although it doesn't sound like much, because 3.5 sounds like, halfway between 3 and 4. But the reality is that GPT-4 is a vastly larger model, first of all. And the basic way these models are put together is that they're trained on large corpuses of data. So there's a lot more data in it. But then they're also, the reason that they pass the Turing test, I mentioned Alan Turing, and can fool us into sort of believing they're human or being more empathetic than humans, is because of other elements in which they're basically trained by humans to react more humanly. So reinforcement learning, like the Atari game, is applied so that because when you start these models and initiate them, the answers they give aren't very human-like. And sometimes, if the data input is small enough, they don't even look like words. And as the data gets bigger, it starts to look like words. To get it to sound human, you have to tell it what's human-like. And so they get trained reinforcement learning by humans. Another example comes to mind is that certain words have become much more common now in applications, letters, writing, because they appear in these models. The word delve is the classic example in English. I used to like the word delve. Now I don't use it in writing, partly because I think people will think I'm using a language model. But it turns out that a lot of the reinforcement learning was done in Nigeria, and the particular version of English they use in Nigeria happens to include the word delve as a very commonly recurring word. So one of the reasons these models say delve a lot of applications I now get with letters use the word delve, is because people in Nigeria trained these models to be more human-like, and the words that they use include the word delve. Anyway, none of that quite answers your question. They put a lot of other guardrails around to try and make sure that the models were much more conservative. But I think the real answer is I think the data was just much, much larger.
Yeah, so I mean, we also start using more and more AI models, and I think what we find is the challenge is that often the data quality and the data quality is not good enough for some of the things we want to do. For example, we use it in Parkinson's disease. We have progression models, we have genetics from the patients, but there's just not enough genetics of patients that have been followed carefully enough over time. And so it is getting there, but I think it's just going to be a matter of time now for actually generating the right data to feed the AI system. And so it's an iterative process, like you said, the patient talking to the AI and force them back. I think it's also with regard to data creation. We need to kind of figure out what are the most appropriate data that can help us to use AI in the best way to actually make real breakthroughs.
Yeah, I think that's a really important point, and one worth making. These emergent properties where the models that start to appear human really only arise with massive data. If you know, and I think the equivalent in, let's say, the world of DNA or RNA or epigenetic models, let's say for AI, we're going to need really massive data to get to the point of seeing these emergent corporate property equivalents that we now see in kind of language.
Can I just ask also, how much of a barrier is access to quality data for the future of AI?
Yeah, I think it's critical, and an even bigger issue might even be the access to compute, because there is a GPU shortage. One of the reasons that NVIDIA has had this very sharp rise, and that there's a lot of concern over where the chips are made and who designs them. From a kind of geopolitical perspective, is that the models are really dependent on both data size and then chips for training, and both of those are becoming a more scarce resource. The tech companies may be the only ones. This is one of the bullets I put at the end. Maybe there's a handful of tech companies that are actually capable of having the money. First of all, some of these models cost $5 billion to train, so it's not the sort of thing my lab can do. Just as an example, or any of us probably here, even pulling our grants on stage, you're not going to get to that kind of money. So then you need access to data. An organization like Google, for example, has all of YouTube as well, so they can actually go into every video on YouTube, pull down the text from video to text or speech to text, and then use that to train. So they have a hidden advantage there, if you like, already. So data size and compute together are going to be the limiting factors.
No, I just want to update for this young audience. Many U.S. universities, at least I know Yale, has been putting a lot of effort to invest in AI. We created a $500 million budget. One point of the budget is to address the data issue, especially medical AI. There are lots of confidential information, and how good AI is depends on how good data you're feeding to them. And we are building our even own the AI cloud, so to speak, a close network with 5 other Eastern Coast universities. And we use hydro plant, green energy.
Yeah, I think that's actually a really important point I was going to make it a moment ago. If we leave the power just in the hands of the tech companies, they're ultimately their aim is to improve shareholder value. Right. Of course, that often results in good things for the world, but not always. And so I think it's really important that academic institutions come together, because that's the only way they would manage to be able to build compute resources they can all use, and academic or not-for-profit institutions, so that the models aren't entirely controlled in the private sector.
So now come one realistic problem for the students. If they like to study bioscience, should they also learn computer as well? Look like that you cannot be an excellent scientist without certain knowledge of an AI expert, just like yourself.
Yeah, I think it is actually a really good idea to have at least some basic knowledge of coding. It's partly a reflection of what my lab looks like, but it's now been many years since I had a pure wet lab scientist come to the lab. I often have mostly wet lab scientists, but even I spoke to one new student this week, and I felt that maybe she had done less computing than most of the folks in the lab, but even she would say, well, actually in my spare time I've been learning Python, and I'm looking, I can do Bash, and I can do some of my own analysis, and I want to learn to be able to do more. So I do think it's almost like a fundamental skill now in a wet lab to be able to deal with higher throughput data and be able to do at least some basic scripting. The good news is, that I didn't talk about this, that almost nobody anymore writes code without a co-pilot next to them, which is to say a language model writing the code or correcting the code. I mean, for the last 2 years, literally nobody in my lab has written code without a co-pilot or language model helping them do it.
So I think for all of you in the audience, I'm sure you must have all been very impressed about the passion by which our speakers have talked about their research. So truly, to become a scientist, a life scientist, obviously you have to have a passion. So I'd like to ask each one of you, who obviously have a passion, to answer very briefly, what is the major problem you would like to solve going forwards now? You've talked a lot about what you've achieved, but can you just briefly say what would be the major problem that you would like to solve going forward? So maybe start with Anne.
Putting me on the spot.
Ladies first.
Well, I'm a geneticist, and I think one of the conceptual advances that we really need to understand is about variation within the population, and in particular to classic genetic concepts around, they're called variable penetrance and variable expressivity. This is how I alluded to this here, trying to understand why a bunch of people with the same genetic mutation have different manifestations of that mutation, and indeed how offspring that inherit that mutation have different manifestations from each other. So what is the explanation of variation within of particular diseases? And a lot of that will have to do, I think, with regulatory molecules that are acting at these loci, so-called trans factors, many of which will probably be epigenetic.
Thank you, Anne. So maybe Haifan, you'd like to have another go?
Okay, sure. Since I was the last speaker, you probably still remember a few of my words. My last question really is to understand how the entire genome function is integrated together. Just remember that our genes are just few percent of the genome. The vast majority of the genome is essentially still unknown. And without knowing such important parts of the genome, I don't think we are understanding the biology so completely. And in the case of these pioneers, even though we just started discovering it, many of these pioneers and the PV proteins themselves now have been shown to be essential in many types of cancers. That indicates there are even missing cancer mechanisms from the basic understanding level that we don't know. And I hope this will be my question, how the genome is integrated and how pioneer mediate this integration. And with tens of millions of pioneers, I need AI's help. And then together, how can that benefit the clinical application? That's my next question.
Thank you, Haifan. And Lawrence?
Yeah, I still remember when I got this same question when I got hired at Sloan Kettering from Jim Rossman, who went on to win the Nobel Prize for Wiesner, Tiesner's. And I remember I was sitting in the taxi and told him, oh, there's two things I really would like to do. One is really understanding how you make all the cell types from pluripotent cells, and the other thing is, to cure Parkinson's disease. So we didn't really completely get there, but we're getting closer now to actually having an impact. But I think the next two things for me is actually this issue that I alluded to, this timing question. So what really controls time? So why do we get maximum 90 or 100 years old? What controls lifespan? What controls early timing? What are the factors? And I think there's still a huge mystery. We understand very well transcription networks at an early stage, but time is still kind of a mystery. And the other thing is very ambitious, I guess, is really focusing more and more actually on Alzheimer's disease, which is extremely complex because it's not just dopamine neurons, there's many neurons. And we actually think currently that maybe there's some really innovative ways of how we can use microglial cells there. And so that's maybe the goal for maybe the next 10 or 20 years.
Yeah. Your next frontier. So Ian, what's your next frontier?
Yeah, I think I would answer in relation to the genome part of my lab and maybe the last slide I put up there, because I think that we've gotten so much better at sequencing the genome to be able to diagnose disease. We'd love to understand variable penetrance best. So you got that one for us. You got that one solved. We want to be able to also treat and do genome engineering to cure those diseases. And there are some genetic diseases that, for now, that's a reasonable word to use, effective cures. But to do that, we've got to be able to get those really amazing new tools, base editors, prime editors, CRISPR tools, to the right cell at the right time. And so I would love to solve delivery. I remember talking to Andy Fire, his name came up. So I called him up when I was quite new at Stanford, and I had this idea about allele-specific silencing for these diseases, and we did some work in that arena. I asked him, what were the major issues that we need to solve, and he said, there's 5 things you need to solve: delivery, 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 and delivery. So we haven't solved it yet, so we'd love to try and solve it.
Taking science from a slightly different aspect, in Hong Kong recently we had great promotion of entrepreneurship, trying to transform science into a commercial business. I do see that a lot of successful cases here. So I'd like to hear, what is your journey like, from a good scientist into a good entrepreneur and make it into a so-called strong business? So start with Lawrence. I mean, I know that your company was bought by Bayer just a few years ago. So how was the journey like?
I mean, I think it was a journey that kind of naturally flew or emerged from our work. So it was really the passion of actually making a difference. And you can only do that up to a certain level on an academic scale. We talked about billions of dollars now of AI network model. You're just not going to get a grant for that. No? Yeah. And so you need to kind of have a different way to raise funds. And that was really for us the limiting factor. We had a big grant, $15 million was big for us from the state of New York to get all the way to make the cells ready for the clinic. But then it finished. And so it is on, first of all, we need to have more money, but also if we really want to treat millions of people, there are more than 10 million of people with Parkinson's disease, that's never going to happen without really scaling it up. And so we want to have a big partner. And it was the time when stem cells really were kind of at the high time. Not many people have tried it at that entrepreneurial level. So we really dreamed at the time to make what we call the Genentech of cell therapy. So we had like a cardiac program, neuro program, and actually some other programs as well. And I think it's going to trim down on some few companies that succeed, but I think it's just this next level of the dream. So I think many people ask me, so why do you then not go into the company? But I think that's for me not as attractive because so many people do that. It's a huge effort, and there are other people that do that probably better. But to give it the push, to give the idea the push to actually turn into a company, that's for me one of the most exciting parts. And then go back to the lab now and work on the next big idea.
You and maybe I take the angle slightly different. You and I sit on the same company, the AstraZeneca board of director. How do big companies like this take the science into so-called the patient, but it's not just for profit, but also try to make a difference to the humankind?
Yeah, I mean, I think at the end of the day, we've talked a little bit about this almost like academic versus industry perspective, but the reality is that the people who go into work every day in those companies, whether it's a small biotech or a big pharma company, aren't going in saying, I wonder how I can make more money today. I mean, there are people, I'm sure, on the finance side of those companies who do that, but the scientists aren't doing that. And for the most part, they want to change the world the same way everyone else does. They want to cure disease. And so I think that journey is, and you beautifully described here, and with this really lovely work, it is a journey. And so many things begin, even for big pharma, like AstraZeneca, like Bayer, it begins in small labs, often in academia, sometimes in small biotechs. At some point, it has to leave academia, and then sometimes postdocs go out, sometimes the PIs go out too, and continue that journey. It's certainly very fun to be able to take that journey with the idea of whether you remain in academia or not, and then eventually, potentially, into a very big pharma company that can really distribute it to the world. It's I think, very worthwhile.
Thank you. Anne?
Yeah, I would echo that. The key thing, I think, is about porosity. It's about the movement of people from different sectors in a smooth and comfortable way. And I think actually AstraZeneca epitomizes that really beautifully in the way that they've integrated into my ecosystem at the University of Cambridge, where AstraZeneca just landed slap bang in the middle of our academic environment. And I think at the beginning, everybody was sort of, oh my goodness, there was a little bit of concern about what this would look like. But actually, it was quite remarkable watching within a very short period of time the trust that was built up between academics and our industrial colleagues who were really excited about talking to academics, and that brought researchers into that industry landscape in a very quite remarkable way. And then the third thing, I think, that, so there's this porosity, there's the synthesis of an enabling ecosystem. You know, we in Cambridge, I mean, certainly on the east and the west coast of the US, they're doing this absolutely beautifully and seamlessly. But that end-to-end journey from fundamental research into its application and commercialization is really having an ecosystem where that is visible to young people coming into the system is really, really important. And then the final thing, which I am very excited about, because I see our young people doing this much better than my generation, is that not being afraid to take risks, that, you know, wanting to try something and it being okay if it doesn't work. And then moving on and trying something else. It's aligned with the porosity, moving from academia into industry, back into academia again, setting up a small company, it may be failing, setting up another one that might fail not quite so badly, and then starting another one that works, based on interacting with colleagues, being supported by academics, engaging with industrial colleagues that are in the landscape. So it's porosity, creating an enabling landscape, and not being afraid to take risks.
So taking that note, I think that our time is almost up. To the student, I would like to say that life science is great fun. It's an excellent journey that you can travel through from all the way from, you know, the knowledge of the biology to AI to commercialization, and then it's actually a very rewarding experience. So, Kathy, would you like to make a final word?
One final word from you, Haifan.
Okay.
Okay. What do you think then? Is it necessary for all basic scientists to make that journey, to make the journey all the way to what often governments want, commercialization and companies?
Well, my simple answer is not all necessary. Everyone should pursue your passion. And whatever you're passionate about, if it's basic research, that's enough for you, stay there. If your passion is to start a biotech company, then go with that passion, follow that passion. For example, at Yale, we have students, including actually one student in my lab. She started the Yale Biotech Club. Basically, it's an apprenticeship kind of organization that allows students to get into biotech. And you know, there's a whole big place called the Yale Entrepreneurial Club that link with business school. But I see only about maybe 25% of students truly have that passion. And for those students who have that passion, they did very well. But if you're just there just to try out your life or something, be prepared that, you know, there are lots of other opportunities you can consider. And my only advice is follow your passion in research.
Well, on those very, very wise words, so we say thank you to our panel, and thank you to all the audience, and I hope the young people in the audience, you enjoyed that session, and hopefully you'll be inspired to take up life sciences.
Thank you very much. Thanks a lot for the insightful sharing. May I invite all the guests on stage to have a photo together. Could you please rise, and then we can have a photo together. Okay, so let's get ready, and then don't forget your big smile. Have a look to the center, please. One more to go. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, one more. One, two, three. 1, 2, 3. Okay, thank you so much. Thank you for the sharing. It's really insightful. And please be seated. So now it's the finale of today's symposium. Ladies and gentlemen, once again, thank you so much for joining our 2024 Future Science Prize Week and the Science Symposium. Tomorrow's topic will cover physics, mathematics, and computer science. I hope you enjoyed today's program as much as I did. For those who have registered for the Hong Kong Science Museum Guide Tour, please follow the instructions from our helpers. For those who will be joining the welcome dinner, please remember to gather in front of the entrance at 4:55, as we have arranged a shuttle bus for you. See you around during the Future Science Prize Week. Thank you.